What is the sound of perfect stillness? What does it feel like when the universe holds its breath, when every atom ceases its endless dance? Tonight, we wonder about an impossible cold, a temperature so profound it lies at the very floor of existence itself. We ask, what if our Earth, in all its warmth and life, were to touch absolute zero? There is no need to brace for this cold. We will explore this question together, from a place of warmth and comfort. So before our journey begins, allow yourself to settle in. Let the weight of your body be held. Release the tension in your shoulders and feel the gentle rhythm of your own breath. Let it be your anchor in the quiet of this moment. Before we drift into this peaceful thought, I wonder where you are listening from tonight. If you feel inclined, you might share your city and the time of night in the comments below. A quiet signal from your corner of the world to mine. Tonight, our journey begins not with a cataclysm, but with a whisper. We will explore a concept that is both deeply simple and profoundly complex, tracing the path of our world into a state of ultimate quiet. We begin by listening to the first whispers of an absolute cold. Let us begin with a feeling you already know. Think of a cool autumn evening, the kind where the air holds a crispness that feels clean and new. When you feel that coolness on your skin, what you are truly experiencing is not the arrival of something called cold, but rather the departure of something else. Heat. Heat, in its most fundamental sense, is simply motion. It is the frantic, invisible dance of atoms and molecules in the air, in the ground, and within your own body. The faster they vibrate and jostle against one another, the more heat or thermal energy they possess. A warm summer day is a world alive with this microscopic, chaotic ballet. The air molecules are energetic, moving rapidly and transferring that energy to everything they touch. But as evening falls, the Earth gently radiates its warmth out into the empty canvas of space. The ballet slows. The molecules in the air begin to calm, their movements becoming less frantic, more graceful. This slowing is what we perceive as cooling. It is a process of becoming still. This idea that cold is simply the absence of heat is the gentle foundation upon which our entire journey rests. It is not an invasive force, but a profound quietude. Imagine a room filled with 1,000 ringing bells. The sound is immense, a chorus of chaotic energy. Warmth is like this, a constant energetic vibration. Now imagine that one by one, the bells cease to ring. The sound does not disappear because a silence has entered the room. It fades because the source of the sound, the motion of the bells, is coming to an end. Cold is this growing silence. It is the gradual cessation of the universe's own internal ringing. Every object in the cosmos, from the most distant star to the chair you are resting in, possesses some measure of this internal motion. And every object, if left to its own devices in the vast, empty spaces between stars, will slowly radiate its heat away, its own molecular dance becoming ever more tranquil. Our planet, the Earth, is a wonderfully warm and energetic place, constantly bathed in the energy of our sun. It is a world where the dance of molecules is vibrant and complex, allowing for oceans to flow, winds to blow, and life itself to exist. But for our journey tonight, we will imagine this solar warmth fading away. We will imagine our world being allowed to slowly, peacefully radiate its own energy into the void, its own bells falling silent one by one. This is the first step, to understand that we are not descending into a hostile presence, but rather, We are exploring a path toward an ultimate and perfect absence of motion. We are following the slow, gentle journey of energy as it departs, leaving behind a state of profound and dreamlike stillness. From this simple, intuitive beginning, we can now set our sights on the destination of our journey, the final, quietest note in the cosmic symphony. Having understood cold as a gradual quieting of molecular motion, we can now gently approach the horizon of our journey, a concept known as absolute zero. It is the theoretical end of the line, the point at which this quieting becomes complete. It is the temperature at which all the classical motion of particles ceases entirely. It is the floor of the universe, the very bottom of the cosmic scale of heat. There is no colder state possible because there is no state that is more still. To measure this, scientists conceived of a scale that begins at this very floor. You may be familiar with Fahrenheit or Celsius, scales that are based on the freezing and boiling points of water, anchored to our everyday human experience. But the Kelvin scale is different. It is more fundamental. Its starting point, 0 Kelvin, is absolute zero itself. It is not an arbitrary point. It is the true, physical end of the road for thermal energy. On this scale, water freezes at a relatively warm 273.15 Kelvin. The room you are in is likely around 295 Kelvin. Even the coldest, most remote places on Earth, in the depths of an Antarctic winter, rarely fall below 180 Kelvin. These temperatures, which feel so extreme to us, are still a vast distance from the true quiet of zero. Absolute zero corresponds to minus 273.15 degrees on the Celsius scale, or minus 459.67 degrees Fahrenheit. But these numbers are less important than the idea they represent. They represent the ultimate stillness. Imagine the atoms of a solid substance as tiny spheres connected by invisible springs, constantly vibrating and jostling against each other. This is the nature of their heat. As the substance cools, these vibrations lessen. The spheres move less and less, their dance becoming slower, more subdued. Absolute zero is the theoretical point where this vibrational motion stops completely. The spheres become perfectly still, their kinetic energy reduced to its lowest possible value. It is a state of perfect internal order. The concept was first theorized by the scientist William Thomson, who would later become Lord Kelvin in the mid-19th century. He observed that as gases were cooled, their pressure decreased in a predictable, linear way. He extrapolated this line backward, and he realized that it must, at some point, reach a pressure of zero. This theoretical point, where the energy of the gas particles would be nil, was the first mathematical signpost pointing toward absolute zero. It was a destination on a map of physics, long before we had the technology to even begin the journey toward it. So, as we proceed, let us hold this concept gently in our minds. Absolute zero is not a place, but a state. It is a state of maximum quiet, of minimum energy. It is the universe with its breath held. It is the final, silent note after the symphony of motion has ended. This is the state our Earth will, in our shared thought experiment, slowly and peacefully approach. We have established our destination, the very definition of the absolute, and now we can begin to imagine the first profound changes that would occur as our world begins its descent. Our journey from the familiar warmth of our world to the profound stillness of absolute zero begins, as all grand journeys do, with a single step. We will not leap to the end, but rather, we will observe the first, most immediate consequences as the temperature begins its relentless, steady fall. The first part of our world to feel this change would be the most delicate and ethereal, the atmosphere. The air we breathe, this invisible ocean in which we live, is a mixture of gases, primarily nitrogen, oxygen, argon, and a small amount of others. These gases are in a constant state of energetic motion, their molecules darting and colliding at hundreds of miles per hour. This energy is what keeps our atmosphere a gas, pushing back against gravity and extending for miles above the surface. But as the Earth begins to lose its heat, this energetic dance will slow. The molecules of the air will begin to move more sluggishly, their collisions becoming less frequent and less forceful. As they lose energy, they will be less able to resist the persistent pull of Earth's gravity. Imagine the sky as a vast, invisible ceiling held up by the tireless motion of countless tiny pillars. As the pillars lose their strength, the ceiling begins to lower. So it would be with our atmosphere. It would begin to contract, to shrink, the upper layers pressing down upon the lower ones with a gentle but inexorable weight. The sky would literally begin to get closer. The air at sea level, which we experience as a comfortable pressure, would become denser and thicker. Breathing would feel different, the air heavier in the lungs. High on the mountaintops, the thin air would grow thinner still, rapidly becoming a near vacuum as the atmospheric blanket pulls away, sinking toward the surface. This would be the first great separation. The boundary between our world and the vacuum of space would become sharper, more defined. The gentle, fading blue of our upper atmosphere would vanish, replaced by the stark, star-dusted blackness of the cosmos, a view once reserved for astronauts, now visible from the ground. The world would feel smaller, enclosed beneath a shrinking dome of its own air. This initial cooling would also have a profound effect on the weather. All the dynamic processes of our atmosphere, the winds, the clouds, the storms, are driven by differences in temperature. The contrast between the warm equator and the cold poles creates the great currents that circulate our air. But in a world that is cooling uniformly, these differences would begin to vanish. The engine of the weather would sputter and slow. The winds would soften from gales to breezes and then to mere whispers until a great calm settled over the entire planet. The skies would become unnervingly clear, as all the water vapor, the substance of clouds, is one of the first things to surrender to the cold, freezing and falling to the ground as a fine, glittering frost. The first stage of our planet's transformation, then, is a great settling. It is the calming of the atmospheric sea, the silencing of the winds, and the clearing of the skies, preparing the way for an even more dramatic change. As the great calm settles upon the Earth and the atmosphere continues to cool, we move beyond simple contraction into a far more profound transformation. The slowing dance of the air molecules will reach a critical point, a threshold where their lack of energy no longer allows them to remain as a gas. They will begin to undergo a phase change, a transition from gas to liquid. This is the beginning of the great condensation. The first to surrender would be the trace gases with higher boiling points. Carbon dioxide would be among the first, transforming from an invisible gas into a delicate white frost, like the frost that forms on a window pane. But this would cover the entire world. It would be a fine, shimmering layer of dry ice, blanketing landscapes in a pale, ethereal powder. But the main components of our air, nitrogen and oxygen, would hold out longer. Nitrogen, which makes up about 78% of our atmosphere, resists this change until the temperature drops to around 77 Kelvin. Oxygen, the vital 21%, waits until about 90 Kelvin. In our journey, as the planet's temperature continues its steady descent, it will cross these thresholds. First, as it passes 90 Kelvin, the oxygen in the air will begin to condense. It would manifest not as a frost, but as a rain. A gentle pale blue rain would begin to fall all across the globe, from the highest mountains to the lowest valleys. This would not be water, but liquid oxygen. It would be a strange, quiet drizzle that would pool on the surface, forming shimmering, pale blue puddles in the hollows of the landscape. Then, as the temperature continued to fall, passing 77 Kelvin, the nitrogen would follow. A clear, colorless rain of liquid nitrogen would begin to fall from the ever-thinning sky. For a time, these two strange rains would fall together, mingling on the ground. The sky, once an ocean of invisible gas, would be emptying itself onto the surface of the planet. The atmospheric pressure would plummet. What little air remained in a gaseous state would be thin and unbreathable. The familiar blue of our sky, caused by the scattering of sunlight by air molecules, would be gone. The sun would be a sharp, white disk in a black, star-filled sky, even at midday. The great condensation would be a silent, global event. It would be the atmosphere surrendering its form, its very state of being, to the encroaching cold. The world's surface would become an alien landscape, slick with cryogenic fluids, under a sky that is rapidly becoming a vacuum. This process connects the fate of the atmosphere directly to the surface below, setting the stage for the next, even stranger phase of this transformation, a brief and beautiful moment when the Earth wears an ocean of air. Following the strange, silent rains of oxygen and nitrogen, our world would enter a brief, transitional phase of breathtaking and alien beauty. Before the cold becomes so profound that it freezes these new liquids solid, there would be a time when the Earth's surface is covered by a shallow, shimmering ocean of what was once our sky. The entire atmosphere, condensed and collected, would form a global sea of liquid air. Its depth would vary with the topography of the land, pooling deeper in the great basins of the oceans and shallower on the continents. It is estimated that if the entire atmosphere were to liquefy, it would cover the planet in a layer roughly 10 meters, or about 33 feet, deep. This new ocean would be a mixture of pale blue liquid oxygen and colorless liquid nitrogen, swirling together in silent, slow-moving currents. It would be a world submerged. The great forests of the planet would stand as silent, crystalline sculptures, their lower trunks disappearing into this clear, cryogenic sea. The cities of humanity would become sunken ruins, their streets and avenues flowing not with water, but with the very air we once breathed. This liquid air would be incredibly cold, and its touch would instantly freeze anything warmer than it. The ground beneath it, already brittle with cold, would be flash-frozen to the consistency of glass. Any remaining warmth from the Earth's interior would be unable to penetrate this insulating layer of liquid. The planet would be sealed. Visually, the effect would be mesmerizing. Sunlight, striking this new global ocean, would refract and shimmer. The world would sparkle with a strange liquid light, its surface a mosaic of pale blue and crystal clear, constantly shifting. There would be no waves in this ocean, for there would be no wind. There would be no sound, for the medium that carries sound is now this silent liquid. It would be a world of profound stillness, yet also of a strange, flowing beauty. This phase, however, would be fleeting. It is a mere pause in the journey downward. It is the final moment before the last vestiges of motion in our atmosphere are extinguished. This ethereal image of a world covered in an ocean of air serves as a crucial bridge. It connects the gaseous sky we know to the solid, frozen shell that the Earth is destined to become, as the temperature continues its inexorable fall toward absolute zero. It is the last moment of fluidity, before the world locks into its final, solid form. The beautiful, fleeting moment of a world covered in an ocean of liquid air must come to an end. As the temperature continues to fall, it will cross the final thresholds for our atmosphere. At about 63 Kelvin, the liquid nitrogen will freeze, turning into a clear, solid ice. Then, at around 54 Kelvin, the liquid oxygen will also solidify, becoming a pale blue, crystalline solid. The entire atmosphere, once a gas, then a liquid, will now become a solid layer of ice, blanketing the entire planet. This layer, a mixture of nitrogen and oxygen ice, would coat everything. It would be a final, global snowfall, a snowfall of what was once the sky itself. The world would be encased in a shell of frozen air. With this final transformation, the most profound and absolute silence would descend upon the earth. Sound, as we experience it, is a vibration, a pressure wave that travels through a medium, most commonly the air. The sound of the wind, the call of a bird, the sound of your own voice, all are disturbances propagating through the gaseous ocean of our atmosphere. But now, that ocean is gone. First it became a liquid, and now it is a solid. There is no more air to carry a wave of sound. The very concept of sound in an open space would cease to exist. A rock falling from a cliff, if anything were to move it, would strike the ground without a whisper. A volcanic eruption, driven by the last vestiges of internal heat, would be a grand, silent spectacle of light and motion, but utterly without the thunderous roar we would expect. The silence would be more complete than any we can imagine on Earth today. Even in the most advanced anechoic chambers, soundproof rooms designed to absorb all echoes, you can still hear the faint sounds of your own body, your heartbeat, your breathing. But on a world with no atmosphere, even these sounds would have no medium to travel through from your body to your ears, assuming you could exist there. The planet would become a realm of perfect quiet. This silence marks a fundamental shift in our journey. We have now fully dealt with the fate of the atmosphere. It has been condensed, liquefied, and finally frozen solid onto the surface. The sky has become one with the land. This act of silencing the world prepares us for the next stage of our exploration. With the air now a static, solid layer, our focus can shift to the next great system of our planet, the vast, deep oceans of water, and how they too will surrender to the encroaching stillness. Having witnessed the sky fall and freeze, blanketing the world in a profound and utter silence, our journey now takes us to the great bodies of water that define our planet. The oceans, vast reservoirs of warmth and life, must now face the same inexorable descent into stillness. The oceans of our world are immense stores of thermal energy, far greater than the atmosphere. For millennia, they have absorbed the light of the sun, and their currents have acted as a global circulatory system, distributing warmth around the planet. Their response to the encroaching cold would therefore be slow, majestic, and powerful. As the atmosphere above them vanishes and the temperature plummets, the surface of the oceans would begin to radiate their heat away into the blackness of space. The process would begin at the surface, the boundary layer between the water and the near vacuum above. The top few inches of the ocean would cool rapidly, their molecules slowing their energetic dance. Unlike most substances, water has a peculiar and wonderful property. It becomes densest not at its freezing point, but at 4 degrees Celsius, or about 39 degrees Fahrenheit. As the surface water cools, it becomes heavier and sinks, pushing the warmer water from below up to the surface. This process, called convection, is a powerful mechanism. It means that the entire body of water must be cooled before the surface can begin to freeze. The oceans would, in effect, be constantly churning themselves, bringing their deep reserves of warmth to the surface to be radiated away. This would be a long and stately process. The sheer volume of water in Earth's oceans means that the amount of heat to be shed is astronomical. For a very long time, the oceans would be the warmest things on the planet, valiantly resisting the cold. But their store of energy is finite. Slowly but surely, the entire column of water, from the sunlit surface to the crushing darkness of the abyssal plains, would cool. The great ocean currents, like the Gulf Stream, which are driven by differences in temperature and salinity, would slow to a crawl and eventually stop altogether. The ocean would become still and stratified. Eventually, the entire body of the ocean, all 326 million cubic miles of it, would reach a uniform temperature of 4 degrees Celsius. It is only after this point, when the entire reservoir of warmth has been spent, that the final, dramatic stage can begin. The surface water, now cooling below 4 degrees Celsius, would become less dense again. It would float on top, no longer sinking, creating a stable cold layer at the very surface. This layer would then continue its journey down the thermometer, past 3, then 2, then 1 degree, until it reached the fateful temperature of 0 Celsius, the freezing point of water. This slow, methodical cooling, this majestic surrender of millennia of stored sunlight, sets the stage for the planet's next great transformation, the solidifying of its vast, blue heart. Once the vast oceans have been uniformly cooled and the surface layer reaches 0 degrees Celsius, the next phase change begins. The water molecules, their dance now slow and graceful, would begin to lock themselves into a highly ordered, crystalline structure. They would begin to form ice. Because ice is less dense than liquid water, another of water's wonderfully unique properties, it would float. The freezing process would therefore happen from the top down. A thin, transparent sheet of ice would first form on the surface of the silent, still oceans. This initial layer would rapidly thicken as the cold continued to draw heat up through the ice itself. The ice sheet would grow downwards, meter by meter, its crystalline front descending into the dark, liquid water below. The process would be inexorable. The ice layer would become 100 meters thick, then 1,000. The remaining liquid water would be trapped beneath an ever-thickening ceiling of ice. The immense pressure of the growing ice sheet from above, and the expansion of the water as it freezes, would create tremendous stresses. Great cracks and fissures would silently form and propagate through the ice crust, cosmic-scale versions of the cracks in a frozen pond. Eventually, the freezing front would reach the very bottom of the ocean. It would touch the abyssal plains, the mid-ocean ridges, and the deepest trenches, like the Mariana Trench. The entire volume of the Earth's oceans would become one single, solid block of ice. It would be a planetary transformation of staggering scale. The Earth, from a distance, would lose its familiar marbled blue and white appearance. It would become a perfect, polished sphere of white. The ice surface would be incredibly smooth, smoother than any surface found in nature today, as there would be no wind to create texture, no waves to sculpt it. It would be a planet-sized billiard ball of ice. Under the faint light of the distant sun, this new surface would be dazzlingly reflective. Earth would become far more brilliant than it is today, its albedo, or reflectivity, approaching 100%. It would shine in the darkness of space like a bright, white star. The very geography of the planet would be redefined. The distinction between continent and ocean would be blurred, all of it trapped beneath a continuous shell of frozen atmosphere, and below that, a deep, global cryosphere of water ice. The planet's dynamic, flowing heart of water would have become a solid, static, crystalline monument. This transformation of the oceans from a dynamic fluid to a solid block of ice is one of the most significant steps in our journey, fundamentally altering not just the planet's appearance, but also the physical forces at play, leading us to consider the immense pressures building in the deep. With the oceans now frozen into a solid, planet-encompassing block of ice, our attention is drawn from the surface to the immense pressures that would build in the deep. Water, as it freezes, expands by about 9%. In a confined space, this expansion can exert a force that is almost irresistible. Now, imagine this force acting on a global scale. As the ice sheet thickened from the top down, the remaining liquid water below would have been trapped between the descending ice ceiling and the unyielding ocean floor. The pressure in this shrinking volume of liquid would have become astronomical, far greater than the pressures we see today in the deepest parts of the ocean, which are already immense. Under these colossal pressures, the very nature of ice itself would change. The familiar ice we see in our world, known to scientists as ice IH, has a hexagonal crystal structure. But this is only one of at least 19 known forms of ice, each with a different crystal structure and different properties, forming under different conditions of temperature and pressure. Deep within the frozen ocean of our hypothetical Earth, these exotic forms of ice would dominate. As the pressure mounted in the final pockets of liquid water, they would not freeze into the familiar, buoyant ice, IH. Instead, they would transform into denser forms of ice, such as Ice 3, Ice 5, or Ice 6. These are known as high-pressure ice polymorphs. Unlike the ice we know, these forms are denser than liquid water. Their molecules are packed together more tightly in different crystalline arrangements. So, at the very bottom of our newly frozen oceans, resting on the sea floor, would be layers of these strange, dense ices. The final freezing of the oceans would therefore not be a simple process, but a complex layering of different types of ice, a planetary scale lesson in solid-state physics. The pressure would not only affect the ice, it would be transmitted directly to the ocean floor. The entire crust of the Earth beneath the oceans would be subjected to a new and immense weight from the expanded ice, a uniform pressure that would stress the tectonic plates in ways they have never before experienced. The transformation of the oceans, therefore, is not just a surface phenomenon, it is a geological event. It connects the freezing of the water to the very foundations of the planet's crust, altering the balance of forces that have shaped our world for eons. The story of the cold has now moved from the air to the water, and now it begins to penetrate the rock itself, setting the stage for the changes that will sweep across the continents. Before we leave the frozen oceans behind and turn our gaze to the continents, it is worth pausing to reflect on a profound consequence of this great freezing: the absolute and final end of the water cycle. The water cycle is the continuous movement of water on, above, and below the surface of the Earth. It is a constant, dynamic process of evaporation, condensation, precipitation, and collection. It is the engine of our climate and the lifeblood of our ecosystems. Sunlight warms the surface of the oceans, causing water to evaporate and rise as vapor. This vapor travels on the winds, gathers into clouds, and eventually cools and condenses to fall as rain or snow over land and sea. This water then flows through rivers, seeps into the ground, and ultimately makes its way back to the oceans, beginning the cycle anew. It is a system of perpetual motion, a planetary-scale circulatory system that has been in operation for billions of years. But on our world approaching absolute zero, every single component of this cycle would cease. Evaporation would be impossible, as there is no liquid water and not nearly enough energy to turn ice into vapor. With no water vapor, there can be no clouds, no fog, no mist. The skies would be eternally, perfectly clear. With no clouds, there can be no precipitation, no rain, no snow, no hail. The very concept of weather would be meaningless. The great rivers of the world, the Amazon, the Nile, the Yangtze, would be frozen solid, their channels becoming static ribbons of ice. The flow of water from the continents back to the sea would stop forever. Groundwater would be frozen in the soil. The entire system, in all its beautiful complexity, would be locked in a state of perfect stasis. All water on the planet would become part of the cryosphere, the domain of frozen water. This is more than a physical change. It is the cessation of one of the planet's most fundamental processes. It represents the end of change, the end of flow, the end of the dynamic interplay between ocean, atmosphere, and land. It is a quiet meditation on the processes we take for granted, and how their absence transforms our world into something static and unchanging, preparing our minds to consider a planet whose very identity has been rewritten. Let us now pull our perspective away from the surface of our transformed world and travel far out into the silent darkness of the solar system. Let us look back upon our home from a great distance, as the astronomer Carl Sagan once invited us to do, and see what it has become. The iconic image of Earth from space, the pale blue dot, is a symbol of life, warmth, and fragility. It is a marble of swirling white clouds, deep blue oceans, and continents of brown and green. This image is a portrait of a dynamic, living world, defined by its liquid water and its gaseous atmosphere. But the Earth, on its journey to absolute zero, would present a very different face to the cosmos. The deep, life-giving blue of the oceans would be gone, replaced by the stark, brilliant white of a global ice sheet. The gentle swirling patterns of clouds would have vanished, as the entire water cycle has ceased. The familiar colors of the continents would be buried, hidden beneath the final, shimmering layer of frozen nitrogen and oxygen ice that was once our atmosphere. From space, Earth would be a perfect, unblemished sphere of white, with a slightly bluish tint from the solid oxygen. It would be eerily smooth and uniform. With an almost perfect albedo, it would reflect nearly all the sunlight that struck it, making it shine with a startling, diamond-like brilliance against the black velvet of space. It would be a far brighter object in our sky than Venus, a serene and steady beacon of reflected light. This new appearance would be a mask of perfect simplicity, hiding the complex history and geography that lies frozen beneath. An alien astronomer observing our solar system would not see a world teeming with potential for life. They would see a planet that appears to be a simple ice world, perhaps a captured rogue planet from the cold, outer reaches of the solar system. They would have no immediate way of knowing about the cities, the forests, the mountains, and the deep history of evolution locked in stasis below the crystalline shell. The planet's identity would have been fundamentally rewritten. It is no longer a pale blue dot, a testament to the life-giving properties of liquid water. It has become a pale white jewel, a testament to the universal laws of physics in the presence of extreme cold. This cosmic perspective, this image of a changed and brilliantly sterile world, provides a moment of closure for our exploration of the planet's fluids. It solidifies the external transformation in our minds and prepares us to journey back to the surface, to turn our attention inward, to the very rock and soil of the continents themselves. Having watched the atmosphere and oceans transform into a solid, silent, crystalline shell, our journey now penetrates deeper. We move from the fluids that cover our world to the solid ground beneath our feet. The continents, the seemingly eternal and unyielding rock, must now face their own surrender to the absolute cold. As the profound cold seeps past the newly formed layers of frozen atmosphere and frozen ocean, it begins to permeate the continents. The rocks, soil, and mountains, which we think of as the very symbols of permanence, would begin a slow and dramatic transformation. The guiding principle here is a simple one: thermal contraction. Just as most materials expand when heated, they contract when cooled. The atoms within a solid, like rock, vibrate with thermal energy. As this energy is removed, the vibrations lessen, and the atoms settle closer together, causing the entire object to shrink. This process would begin at the surface of the continents. The upper layers of the Earth's crust would cool first, and they would begin to contract. The problem is that the rock deeper down, still retaining some of the planet's internal warmth, would not be contracting at the same rate. This differential cooling would create immense and unbearable tension within the crust. Furthermore, rocks and minerals are not uniform substances. A piece of granite, for instance, is a composite of different minerals like quartz, feldspar, and mica. Each of these minerals has a different coefficient of thermal expansion. They shrink at different rates as they get colder. So even within a single boulder, internal stresses would begin to build as some mineral grains try to shrink faster than their neighbors. The rock would essentially be tearing itself apart from the inside out. At the same time, any moisture trapped in the soil or in the pores of the rock would freeze and expand, a process known as frost heaving. This would exert another powerful force, wedging cracks open and shattering the rock from within. But the most significant change would be in the properties of the rock itself. As materials become extremely cold, they lose their ductility, their ability to bend or deform slightly under stress. They become incredibly brittle. Think of the difference between a piece of warm taffy and a glass icicle. The rock of the Earth's crust would lose all its faint geological flexibility and become as fragile as glass. The ground beneath our feet would be primed for a great shattering. It would be a world wound up like a spring, the tension building silently within the crystalline structure of the very stone, waiting for the inevitable moment of release. This sets the stage for a dramatic, albeit silent, reshaping of the entire surface of the planet. With the Earth's crust now incredibly brittle and riddled with unimaginable thermal stress, the inevitable must happen. The stored tension would overcome the cohesive strength of the rock, and the surface of the continents would begin to fracture. This would not be a singular event, but a continuous, cascading process of shattering, a silent, slow-motion cataclysm. The first fractures would likely appear as small, hairline cracks on the surface. But these cracks would instantly release the tension in the surrounding rock, causing that tension to concentrate at the tip of the crack. This would drive the crack forward with unstoppable force, propagating through the brittle crust for hundreds or even thousands of miles. Great chasms, far deeper and wider than the Grand Canyon, would silently split the continents apart. They would form in an instant, but without a sound, as there would be no air to carry the noise of 1 billion tons of rending rock. The landscape of the Earth would be rewritten. Mountain ranges would be split in two. Vast plains would be sundered by intricate, geometric networks of new canyons. The patterns of these cracks would be fractal, like the patterns seen in shattered glass or a drying lake bed, but on a planetary scale. This process is known as thermal shock, and it is what causes a hot glass to shatter if plunged into cold water. On our frozen Earth, this would be the same principle, enacted over an entire world. The scale of this fracturing is difficult to comprehend. The shrinking of the crust would be significant. It is estimated that the Earth's radius could decrease by several miles due to thermal contraction alone. This shrinking would cause the surface to buckle and break in spectacular ways. Fault lines that have been dormant for millions of years would move, not with the grinding friction that causes earthquakes, but with the clean, silent snap of breaking glass. Entire tectonic plates, already defined by their boundaries, would likely shatter into smaller, fractured pieces. The world would become a jigsaw puzzle of fractured rock, its surface a testament to the immense power of the cold. Looking down upon this world, one would see the smooth, white shell of frozen gases and water. But this shell would now be marred by a network of vast, dark canyons, revealing the fractured bedrock beneath. It would be a scene of immense, silent violence, a world that has torn itself apart in its final surrender to stillness. This great shattering marks the point where the cold is no longer just a surface effect. It is now a geological force, powerful enough to reshape the very bones of the planet. This deepens our journey, leading us to consider the effects of the cold on the planet's hidden, fiery heart, the mantle. Having fractured the crust, the relentless advance of the cold continues its journey toward the center of the Earth. Below the crust lies the mantle, a thick layer of silicate rock that makes up the majority of our planet's volume. Under normal conditions, the mantle is a place of incredible heat and pressure. While it is technically a solid, over geological timescales, it behaves like an incredibly viscous fluid, like thick tar. It churns in slow, massive convection currents, with hot rock rising from the deep and cooler rock sinking from above. This slow, powerful motion is the engine that drives plate tectonics. It is what moves the continents, builds mountain ranges, and opens ocean basins. It is the very pulse of our planet's geological life. But as the cold from the surface begins to permeate the crust, it will start to leach the heat from the upper layers of the mantle. This cooling will have a profound effect on its viscosity. Just as honey becomes thicker and flows more slowly when it is chilled, the rock of the mantle would become exponentially more viscous as its temperature drops. The great convection currents, the slow churning that has driven geology for billions of years, would begin to slow down. The rising plumes of hot rock would lose their buoyancy. The sinking slabs of cooler rock would meet a medium that is becoming too stiff to move through. The pulse of the Earth would weaken. The movement of the tectonic plates, which float upon this churning mantle, would grind to a halt. The process of continental drift, which has shaped and reshaped the face of our world throughout its history, would cease completely. The continents, already fractured by the surface cold, would become locked in their final positions. The planet's surface would become static. Mountain ranges would no longer be pushed upward. Rift valleys would no longer pull apart. The constant, slow renewal of the Earth's surface would end. Eventually, as the cold penetrated deeper and deeper over unimaginable time scales, the entire mantle would cool and solidify. It would no longer be a viscous fluid, but a rigid, solid rock. The geological engine at the heart of our world would fall silent. The Earth would transition from a dynamic, living planet, geologically speaking, to a dormant, unchanging one. This sleeping of the mantle is a pivotal moment. It marks the end of all the grand, slow processes that have shaped the world we know, connecting the deep interior of the planet to the cessation of all surface activity, leading us to consider the fate of the most dramatic expressions of that activity, are volcanoes. With the Earth's mantle now solidifying and its great convection currents grinding to a halt, the source of one of the planet's most powerful and iconic features is extinguished. Volcanoes, the fiery vents that connect the molten interior to the surface, would be silenced forever. A volcano is a direct expression of the planet's inner heat. It is a place where magma, molten rock from the mantle, finds a path to the surface. Whether it is the gentle, flowing lava of Hawaiian shield volcanoes or the explosive eruptions of stratovolcanoes like Mount St. Helens. All volcanic activity is dependent on a hot, mobile mantle below. As the mantle cools and becomes rigid, the production of magma would cease. The magma chambers that lie beneath active volcanoes, great pools of molten rock, would slowly cool and crystallize, turning into solid granite or gabbro. There would be no more molten material to feed eruptions. The pressure that builds to create an eruption would have no source. The planet's internal plumbing system would freeze solid. The consequences would be seen all across the globe. The ring of fire, the volcanically active belt that encircles the Pacific Ocean, would become just a quiet, frozen mountain range. The great volcanoes that form island chains, like Hawaii, built by a stationary hot spot in the mantle, would stop growing. The mid-ocean ridges, where new crust is formed as tectonic plates pull apart, would become dormant, their volcanic vents freezing over. It would not just be the great volcanoes that are affected. All geothermal activity would cease. Geysers like Old Faithful, driven by water seeping down to be heated by hot rock, would freeze. Hot springs would turn to ice. The faint residual heat that flows from the Earth's interior, a constant, subtle warmth that is always present, would dwindle and disappear as the cold from the surface overwhelmed it. The planet would lose its inner fire. This silencing of the volcanoes is a powerful symbol of the Earth's transition. It is the end of the most dramatic and visible link between the surface world and the planet's deep, energetic core. The fire has gone out. This complete geological shutdown, from the deep mantle to the highest volcanic peak, leads us to a broader reflection on what it means for a world to become, in every sense of the word, geologically dead. The silencing of the volcanoes is the final, dramatic act in a much larger play. The complete cessation of all geological activity on Earth. With the mantle frozen solid and the tectonic plates locked in place, our planet would become a geologically dead world. Let us consider what this truly means. A geologically active world is one that is constantly remaking itself. Mountains are thrust upwards by colliding plates, while erosion wears them down. New crust is born at mid-ocean ridges, while old crust is consumed in subduction zones. Earthquakes release the stress that builds along fault lines. This constant cycle of creation and destruction, of movement and change, is a defining feature of our planet. On our frozen Earth, this cycle would be over. There would be no more earthquakes. The fractured crust would be static, the stresses that cause seismic waves having been released in the great shattering and now locked in a permanent, frozen state. There would be no more mountain building. The slow, patient uplift that creates the Himalayas and the Andes would be finished. The mountains would exist only as frozen monuments, subject to no further change. There would be no more continental drift. The map of the world would be frozen in its final configuration. The processes of erosion, driven by wind and water, would have already ceased with the freezing of the atmosphere and oceans. The landscape, in all its fractured detail, would be perfectly preserved. The Earth would become a museum of its own geology. Every rock, every canyon, every mountain would be frozen in time, a permanent record of the state of the planet at the moment the great cold took hold. This state of geological death is one of profound and absolute permanence. Nothing changes. The surface, which we see as a canvas of slow but constant transformation, would become utterly static. This quiet summary of the planet's internal death serves as a crucial transition. We have taken the stillness from the atmosphere to the oceans, and from the crust to the deep mantle. Now, our journey must logically continue to the very heart of the planet, to explore the fate of its final, most central feature, the Earth's core. Our journey into the solid Earth now takes us to its final destination, the core. At the center of our planet lies a sphere of mostly iron and nickel, separated into two parts. The inner core is a solid ball, about the size of the moon, under immense pressure. Surrounding it is the outer core, a layer of molten iron and nickel, a swirling, convective ocean of liquid metal. The motion within this liquid outer core is the source of one of Earth's most vital and invisible features, its magnetic field. This field, generated by the flow of molten iron in a process known as a geodynamo, extends far out into space, creating a protective bubble around our planet called the magnetosphere. It shields us from the constant stream of charged particles from the sun, the solar wind, and deflects harmful cosmic rays from deep space. It is a silent, invisible guardian that has protected our atmosphere and enabled life to flourish. In our hypothetical scenario, as the cold from the surface propagates inward through the now solid mantle, it would eventually reach the outer core. Over an almost unimaginable length of time, the cold would begin to draw the heat out of this liquid iron. The swirling, convective motions would slow. The geodynamo would weaken. The magnetic field it generates would begin to flicker and fade. Eventually, the outer core itself would begin to solidify. The liquid iron would crystallize, freezing onto the solid inner core, causing the inner core to grow. The process would continue until the entire outer core was frozen solid. The Earth's core would become one single, massive ball of solid iron and nickel. At this moment, the geodynamo would cease to function entirely. The Earth's magnetic field would vanish. The invisible shield would be gone. The planet would be left naked and exposed to the harsh environment of space. Without the magnetic field, the solar wind would strike the upper layers of our frozen atmosphere directly. Over eons, it would slowly strip away the solid nitrogen and oxygen ice, a process called sputtering, eroding the frozen shell molecule by molecule. Our world, now completely solid from its surface to its very center, would have lost its final defense. The end of its internal dynamism would leave it vulnerable to the wider cosmos. This brings our geological journey to a close at the very heart of the planet, and turns our focus from the large-scale structure of our world to the very fabric of matter itself under these extreme conditions. Having explored the profound changes to our planet on a grand geological scale, from the sky to the core, our journey now shifts its focus. We turn from the macroscopic to the microscopic, to explore how the very nature of matter itself begins to behave in strange and wonderful ways as we approach the ultimate stillness of absolute zero. As our hypothetical Earth cools toward absolute zero, every substance on its surface is forced into its lowest energy state, which for most things is a solid. We have already seen this happen with the air and the oceans. But what about all the other materials that make up our world? Everything from the organic compounds in a wooden log to the metallic alloys in a skyscraper would undergo its own unique journey into the cold. The defining characteristic of this journey is the loss of thermal energy, which translates to the quieting of atomic motion. In a liquid, atoms and molecules are able to slide past one another, giving the substance its fluid properties. In a gas, they move freely and chaotically. In a solid, they are typically locked into a fixed position, a crystal lattice, but they still vibrate with thermal energy. As the temperature drops, this vibration is what lessens. Different materials would respond to this in different ways, based on their freezing points and their internal structures. Mercury, the only metal that is liquid at room temperature, would have long since frozen into a solid, silvery metal at 234 Kelvin. Other substances that we think of as robust would reveal their own vulnerabilities to the cold. For example, rubber in a car tire would lose all its elasticity and become as brittle as glass, shattering at the slightest disturbance. The liquid crystal displays in our screens would be frozen into a static, unchanging pattern. The very way materials fail would change. Instead of bending or deforming, almost everything would fail by brittle fracture, snapping cleanly like a dry twig. The world would become a place of extreme fragility. But beyond just freezing, the properties of these solids would continue to change as they grew colder. Their thermal conductivity, their ability to transfer heat, would change dramatically. Their color might even shift slightly. The world would become a vast laboratory, showcasing how the fundamental properties of materials are deeply linked to the thermal energy they contain. This exploration of the various states of matter serves as a gentle introduction to the new and often counterintuitive physics that begins to dominate in the realm of extreme cold. We are moving beyond simple freezing and into a world where the familiar rules of classical physics begin to give way to the more subtle and fascinating laws of the quantum world, preparing us to witness even more profound transformations, such as the emergence of perfect conductivity. As the temperature on our frozen Earth continues to plummet, we enter a realm where matter begins to exhibit truly extraordinary, almost magical properties. One of the most fascinating of these is superconductivity. In any normal electrical conductor, like a copper wire, there is always some resistance to the flow of electricity. This resistance is caused by the electrons, which carry the current, colliding with the vibrating atoms of the wire's crystal lattice. These collisions scatter the electrons and convert some of their energy into heat. This is why electronic devices get warm. It is a form of friction on the microscopic scale. However, in 1911, the Dutch physicist Heike Kamerlingh-Onnes made a remarkable discovery. While studying the properties of mercury at extremely low temperatures, he found that when he cooled it to just over 4 Kelvin, its electrical resistance suddenly vanished completely. An electric current, once started in a ring of superconducting mercury, could flow forever, with no power source to sustain it. The material had entered a new state of matter, a superconducting state. This phenomenon is a purely quantum mechanical effect. At these incredibly low temperatures, the vibrations of the crystal lattice, the source of resistance, become so small and ordered that the electrons can move through the material without being scattered. They do this by pairing up in a special way, forming what are called Cooper pairs. These pairs are able to move through the lattice in a coordinated, collective manner, like a perfectly disciplined group of dancers moving through a silent, stationary crowd. They do not bump into anything and lose no energy. On our Earth approaching absolute zero, many materials would cross their own critical temperature threshold and become superconductors. The planet's crust is rich in metals and metallic compounds. As the cold deepened, vast, continent-sized regions of the Earth could become perfect electrical conductors. Any stray electrical currents, perhaps induced by the final flickers of the dying magnetic field or a passing cosmic ray, could persist for eons, flowing in immense, silent loops through the frozen rock. Another hallmark of superconductors is their ability to expel magnetic fields, a phenomenon known as the Meissner effect. If you were to bring a magnet near a superconductor, it would hover, suspended by an invisible cushion of magnetic force. On our superconducting Earth, this would mean that any interplanetary magnetic fields from the Sun would be perfectly repelled from the surface, creating a complex interplay of magnetic forces around the planet. The world would not only be a perfect conductor, it would also become a perfect diamagnet. This transformation into a superconducting planet is a beautiful example of how the quantum world, usually hidden from our view, can manifest on a macroscopic, even planetary scale in the realm of extreme cold. It introduces us to a world without friction or resistance, a theme that becomes even more profound as we explore another, related state of matter. The journey into the quantum phenomena of the cold does not end with superconductivity. There is another, perhaps even stranger, state of matter that emerges at temperatures just a few degrees above absolute zero: superfluidity. This property was first observed in liquid helium. Helium is a unique element. It is the only substance that remains a liquid all the way down to absolute zero at normal pressures. It never freezes solid. But when liquid helium is cooled below about 2.2 Kelvin, it abruptly transforms into a new kind of liquid, called helium-2, which is a superfluid. A superfluid has zero viscosity. Viscosity is a measure of a liquid's internal friction, its resistance to flow. Honey is very viscous. Water is less so. A superfluid has no resistance to flow at all. It is a liquid without any friction. This leads to some truly bizarre behaviors. A superfluid can flow up and over the walls of its container, seeming to defy gravity. It can seep through microscopic cracks that would be impenetrable to any normal liquid. If you were to stir a cup of superfluid helium, it would, in theory, continue to swirl forever, never slowing down. This frictionless flow is, like superconductivity, a quantum mechanical effect on a large scale. At these low temperatures, the individual helium atoms lose their separate identities. Their quantum wave functions overlap, and they begin to behave as a single, coordinated quantum entity. A significant fraction of the atoms condenses into the lowest possible energy state, and these atoms can move in perfect unison without any internal friction or energy loss. While there is no liquid helium on our hypothetical Earth to demonstrate this, the concept of superfluidity adds another layer to our understanding of this cold, quiet world. It reinforces the theme of the cessation of all friction and all dissipative processes. Superconductivity showed us the frictionless flow of electrons. Superfluidity shows us the frictionless flow of atoms themselves. It is another step toward a state of perfect, lossless motion, a state where things, once set in motion, could continue forever. It speaks to a world where the familiar rules of energy loss and decay have been suspended. The concept of superfluidity, this ultimate expression of fluid motion without resistance, helps to perfect our mental image of a world where all the brakes have been removed, connecting the theme of stillness with the strange, perpetual motions allowed by the quantum world. As we draw ever closer to the theoretical limit of absolute zero, the changes to matter become more subtle, more fundamental. We have seen how electron flow and even atomic flow can become perfect and frictionless. Now, let us consider the very structure of the solid materials that make up our world. Most solids, from salt and sugar to metals and rocks, are crystalline. This means their atoms are arranged in a highly ordered, repeating, three-dimensional pattern called a crystal lattice. You can imagine it as a vast, intricate scaffolding built of atoms. At any temperature above absolute zero, however, this scaffolding is not perfect. It contains two kinds of disorder. First, there are structural imperfections, missing atoms, extra atoms squeezed in, or misalignments in the pattern. Second, and more fundamentally, every atom in the lattice is vibrating with thermal energy. It is not sitting perfectly still at its designated point in the scaffolding. It is oscillating around it. This thermal vibration is a form of disorder. As a substance is cooled toward absolute zero, these thermal vibrations are progressively damped. The oscillations of the atoms become smaller and smaller. The atomic scaffolding becomes more and more rigid, more and more still. At the theoretical point of absolute zero, all of this classical vibrational motion would cease. The crystal lattice would achieve a state of perfect order. Each atom would settle into its proper place with a stillness that is profound and complete. The substance would become, in a sense, a perfect crystal. This state of perfect order is deeply connected to a fundamental concept in physics called entropy. Entropy is, in simple terms, a measure of disorder or randomness in a system. A hot gas, with its atoms moving randomly and chaotically, has very high entropy. A crystalline solid, with its atoms in fixed positions, has much lower entropy. The third law of thermodynamics states that the entropy of a perfect crystal at absolute zero is exactly zero. It is a state of no disorder. Our frozen Earth, in this idealized thought experiment, would become a planet of near-perfect crystals, a world where the inherent randomness of heat has been completely smoothed away, leaving only the pure, geometric order of the atomic lattice. This image of a perfectly ordered world, a world of ultimate structural simplicity, sets the stage for the cessation of not just motion, but of all change itself. With the atoms of our world locked into their perfectly ordered crystal lattices, their vibrational energy reduced to a minimum, we arrive at a profound and final consequence: the end of all chemical reactions. Chemistry is the science of change. It is the story of atoms and molecules rearranging themselves, breaking old bonds and forming new ones. A log burning in a fire, iron rusting in the rain, the complex processes of digestion, all are chemical reactions. And nearly all of these reactions require a certain amount of energy to get started, an energy of activation. Most often, this energy is supplied by heat. The thermal vibrations of molecules cause them to collide with enough force to break their bonds and allow new ones to form. But on a world approaching absolute zero, there is no thermal energy. The atoms and molecules are locked in place, vibrating only with the faint hum of their zero-point energy, which is not enough to initiate chemical change. All chemical processes would grind to a halt. The slow process of oxidation, which we know as rust or corrosion, would cease. A piece of bare iron would remain perfectly shiny for eternity, as the oxygen atoms, frozen solid nearby, would have no energy to react with it. The even slower processes of geological chemistry, the transformation of sediments into rock, the metamorphosis of minerals, would stop. Nothing would decay. The complex organic molecules in a frozen leaf or a wooden beam would be preserved perfectly, indefinitely. There would be no decomposition, no breakdown of complex structures into simpler ones. The Earth would become a static museum of its own chemistry. Every substance, every molecule would be frozen in the state it was in when the cold arrived. This chemical stasis is, in many ways, the ultimate expression of the stillness we have been exploring. Our journey began with the stilling of large-scale motion, the winds and the ocean currents. It progressed to the stilling of geological motion, the drift of continents and the eruption of volcanoes. Then it moved to the microscopic, with the stilling of atomic vibrations in a crystal lattice. Now, we have reached the stilling of atomic interactions. No bonds will form, and no bonds will break. The great dance of chemical change that underlies all of life and all of geology is over. The planet is not just physically static, but chemically inert. This realization brings our exploration of matter to a close and prompts us to lift our gaze outward again, to consider the relationship between this frozen, static world and its one constant companion, the sun. Having frozen our world from its atmosphere to its core and stilled the very dance of chemistry, we now pull our perspective back to see this new Earth in its cosmic context. A silent, crystalline sphere. It is not alone. It continues its eternal orbit around a star that has not changed. The sun still shines. The sun, the fiery heart of our solar system, continues its thermonuclear fusion, pouring out a colossal amount of energy into space every second. A small fraction of that energy has always fallen upon the Earth, warming its surface, driving its climate, and powering its life. In our hypothetical journey, however, the relationship between the Earth and the Sun has been fundamentally broken. The sunlight still arrives. Photons, particles of light that have traveled 93 million miles, still strike the surface of our frozen world. But the Earth is no longer able to receive their warmth. At temperatures near absolute zero, the planet has no capacity to absorb this energy in a way that would raise its overall temperature. Think of trying to fill a cup that is already full. The incoming solar energy would strike the surface, but it would have nowhere to go. The atoms on the surface are already in their lowest possible energy state. They cannot be easily excited by the incoming photons in a way that would translate to heat. The Sun, from the perspective of our frozen Earth, would be transformed from a life-giving source of warmth into a purely visual phenomenon. It would be a bright, sharp-edged disk in the black, airless sky. Its light would be brilliant, but it would carry no heat. It would be like the light of the moon on a cold winter's night, but far more intense. The very concept of a warm, sunny day would be meaningless. The side of the Earth facing the Sun would be bathed in intense light, but it would be no warmer than the side facing away in utter darkness. The Sun has become a celestial observer, a silent witness to the planet's frozen state. It diligently sends its light and energy, as it always has, but the Earth is no longer listening. It has become a closed system, unable to be roused by the star that once governed its every rhythm. This new relationship reframes our understanding of energy. It is not enough for energy to arrive. The object receiving it must be able to absorb it and use it to increase its internal motion. Our Earth, in its state of ultimate stillness, has lost this ability. It sees the light of the Sun, but it cannot feel its warmth. This leads us to a deeper consideration of how light and heat interact with our frozen world. To understand why the Sun's brilliant light would fail to warm our frozen Earth, we must gently explore the nature of heat transfer. There are three primary ways heat moves: conduction, convection, and radiation. Conduction is the transfer of heat through direct contact, like a warm handle on a hot pan. Convection is the transfer of heat through the movement of fluids, like the warm air rising from a heater. On our solid, vacuum-enshrouded Earth, both of these methods are irrelevant on a planetary scale. The only way the Sun's energy can reach the Earth is through radiation. Solar energy travels across the vacuum of space as electromagnetic radiation, primarily visible light, ultraviolet light, and infrared radiation. When this radiation strikes an object, one of three things can happen. It can be reflected, it can be transmitted through the object, or it can be absorbed. It is only the absorbed energy that contributes to heating the object, as it excites the object's molecules and increases their vibration. On our perfectly frozen Earth, the surface is now composed of a smooth, highly uniform layer of frozen nitrogen and oxygen ice, which is incredibly white and reflective. This property is called albedo. A dark object, like asphalt, has a low albedo. It absorbs most of the light that hits it and gets hot. A white object, like fresh snow, has a high albedo. It reflects most of the light and stays cool. Our new Earth would have an albedo approaching 100%. The vast majority of the sunlight striking the planet would be immediately reflected back into space. The Earth would act like a perfect, planet-sized mirror. The small fraction of energy that was not reflected might be absorbed by the very top layer of atoms in the frozen ice. However, at temperatures near absolute zero, materials have an extremely low heat capacity. This means it takes very little energy to change their temperature, but they also have extremely low thermal conductivity. This means any absorbed heat would be trapped in the very top atomic layer and would be immediately radiated away as thermal infrared radiation, without ever having a chance to conduct deeper into the planet and warm its bulk. The energy would arrive and leave almost instantaneously, leaving the planet's overall temperature unchanged. The sun's light would illuminate the Earth, but it would be unable to warm it. The flow of energy would be entirely superficial, a brief touch that leaves no lasting impression of warmth. Let us dwell for a moment on the serene and beautiful image of this new Earth, a world transformed into a near-perfect mirror. With its surface a smooth, unbroken shell of crystalline ice, its ability to reflect light would be unlike anything in our current solar system. This goes beyond the high albedo of fresh snow. It would be a specular reflection, the kind you see in a polished mirror or a still lake. When sunlight strikes a rough surface, like the current Earth with its oceans and forests, the light is scattered in all directions. This is called diffuse reflection. It allows us to see the color and texture of the surface. But when light strikes a perfectly smooth surface, it reflects at a precise and equal angle, preserving the image of the source. Our frozen Earth would act as a vast, convex mirror. An observer in space, positioned at the right angle, would not just see a bright white dot. They would see a distorted but clear reflection of the sun itself, a brilliant glare on the surface of the planet. As the Earth rotated, this bright spot, this specular reflection, would sweep across its face. The rest of the universe would be reflected too, the faint light from the moon, the other planets, and the distant stars would all be mirrored on Earth's polished surface. The planet would be a celestial ornament, its face a constantly changing map of the cosmos around it. The side of the Earth facing away from the sun, the night side, would be a dark mirror. In the absence of an atmosphere to create a sky glow, the stars would be incredibly sharp and bright. And on the surface of the dark Earth, each of those stars would have a tiny, corresponding reflection. The Milky Way would paint a faint, shimmering band across the planet's frozen face. This mirrored quality would create a world of profound visual purity. All the complexity, all the color, all the history of the Earth's surface would be hidden beneath this perfect, reflective mask. The planet would no longer show its own face to the universe. Instead, it would show the universe its own reflection. It would become a passive observer, its identity subsumed by the light of the cosmos it mirrors. This transformation into a mirrored world is a deeply peaceful and aesthetic concept. It speaks of a world that no longer generates its own appearance, but simply reflects the beauty around it. It is a quiet, final state of being, a world that has become a passive part of the celestial scenery, which leads us to consider how all the rhythms of time and season would become meaningless on such a world. Our Earth has rhythms, cycles of change that define our experience of time. The most fundamental of these are the day and the seasons. The rotation of the Earth on its axis gives us day and night. The tilt of that axis relative to our orbit around the Sun gives us the seasons. Summer in a hemisphere occurs when it is tilted toward the Sun, receiving more direct and concentrated sunlight. Winter occurs when it is tilted away. These cycles are entirely dependent on the differential heating of the planet's surface. The contrast between the light of day and the dark of night is also a contrast between warmth and coolness. The difference between summer and winter is a profound change in temperature and weather. On our mirrored world at absolute zero, these concepts would become hollow, meaningless technicalities. The Earth would still rotate. A point on the surface would still pass from sunlight into shadow and back again. But this transition would have no thermal consequence. The temperature would remain fixed at the lowest possible value, regardless of whether the sun was in the sky. The coming of day would simply mean the arrival of a bright light in the sky and a brilliant reflection on the ground. The coming of night would simply mean the vanishing of that light, revealing the reflected stars. There would be no dawn chorus, no evening cooling, just a change in the ambient light. The seasons would be even more meaningless. The Earth would still have its axial tilt. The northern hemisphere would still be tilted toward the sun in July and away from it in January. But this would only change the angle at which the sunlight strikes the mirrored surface. It would not change the temperature by even the smallest fraction of a degree. The long, warm days of summer and the short, cold days of winter would be replaced by a state of perpetual, unchanging cold. The very calendar we have built around these celestial motions would lose its climatic significance. All the biological and social rhythms that are tied to these cycles, the hibernation of animals, the planting of crops, the celebration of seasonal holidays, would be concepts belonging to a forgotten, impossibly dynamic past. Time, in a climatic sense, would stop. Every day would be the same as the last, and every season would be indistinguishable from any other. The planet would be locked in a state of eternal, motionless winter. This complete erasure of the planet's temporal rhythms further solidifies its new identity as a static, unchanging object, leading us to consider the only new influence it might now receive from the cosmos. With the Earth's magnetic field gone and its atmosphere frozen solid, the planet has lost its two primary shields against a constant, silent rain from the cosmos: cosmic rays. Cosmic rays are not actually rays. They are high-energy particles, mostly protons and atomic nuclei, that have been accelerated to nearly the speed of light by distant cosmic events like supernova explosions. The universe is filled with these particles, a constant, low-level flux of incredibly energetic matter. On our current Earth, the magnetosphere deflects most of these particles, and those that make it through are typically stopped by collisions with air molecules in the atmosphere, creating secondary particle showers that are mostly harmless by the time they reach the ground. But on our frozen, unprotected Earth, these cosmic rays would arrive unimpeded. They would strike the solid, frozen surface of the planet directly. Each cosmic ray impact, though tiny, would be an event of immense energy on an atomic scale. A single high-energy proton could slam into the crystal lattice of the frozen nitrogen ice, shattering the molecules in its path and creating a microscopic track of damage. It would be like a microscopic bullet fired into a perfect crystal. Over millions and billions of years, this constant, silent bombardment would begin to alter the very surface of the planet. It would slowly break down the crystalline structure of the frozen atmosphere, making it more amorphous. It would initiate tiny, localized chemical reactions that would otherwise be impossible, creating new, exotic molecules in its wake. This is not a force of warmth or significant change. The energy deposited would be far too small to raise the planet's temperature. Rather, it would be a slow, persistent form of cosmic erosion. It would be the universe's way of leaving its faint, subtle mark on the otherwise unchanging face of the planet. This arrival of cosmic rays is the only new interaction our world has with the cosmos. It is not a dramatic or powerful force, but a faint, patient touch from the wider galaxy, a constant reminder that even in a state of near-perfect stillness and isolation, the Earth is still a part of a larger, active universe. As we conclude our look at the Earth's new relationship with the Sun and the cosmos, let us settle on a final, serene image of what our planet has become. It is no longer a cradle of life, a dynamic engine of geology and climate. It has transformed into something else entirely. It has become a silent, crystalline beacon in the darkness of the solar system. Its defining characteristic is now its brilliant, mirrored surface. It would be one of the most visually stunning objects in the sky for any hypothetical observer on another planet. It would be a point of pure, white light, outshining all other planets. A small, polished jewel orbiting a quiet star. This visual brightness, however, would mask a profound internal stillness. It is a world that has become a monument to the laws of physics. Every aspect of its being, from its fractured crust to its superconducting core to its perfectly ordered crystal lattices, is a direct expression of how matter and energy behave in the absence of heat. It is a planetary-scale demonstration of thermodynamics and quantum mechanics. Its journey is complete. It has shed all of its internal energy, all of its chaotic motion. It has settled into its ground state, its lowest possible energy configuration. In doing so, it has traded the beautiful complexity of life and change for the serene, simple beauty of physical perfection. It is no longer a world of becoming, but a world of being. It simply is. It does not evolve. It does not change. It orbits. It reflects. This new identity is one of quiet dignity. It is not a dead world in a tragic sense, but a world that has achieved a state of ultimate peace and stability. It is a completed work. This final portrait of Earth as a static, reflective monument serves as a gentle conclusion to our exploration of its relationship with the Sun. It solidifies the image of the planet's final, external state and prepares us to turn our gaze inward one last time to consider the fate of the most precious and complex thing our world ever produced, life itself. We have explored the freezing of the sky, the sea, and the stone. We have witnessed the transformation of matter and the altering of our world's place in the cosmos. Now, our journey must turn to the most delicate and intricate phenomenon on our planet: life. We will now gently consider its final, silent chapter. Life, in all its wondrous diversity, is fundamentally a water-based phenomenon. Every living cell, whether it belongs to a bacterium, a giant sequoia, or a human being, is essentially a tiny, organized bag of water containing complex molecules. Water acts as the universal solvent, the medium in which the chemical reactions of life take place. It is this reliance on liquid water that makes life so fragile in the face of extreme cold. As the temperature on our world begins its descent, life would face an insurmountable challenge. The first and most immediate effect would be the freezing of the water within living cells. As water turns to ice, it forms sharp, needle-like crystals. These ice crystals would grow inside the cells, piercing the delicate cell membranes and destroying the intricate internal structures, like the nucleus and the mitochondria. This process, called intracellular ice formation, is devastating and irreversible. It would physically shred the machinery of life from the inside out. For a brief time, some organisms might resist. Certain insects, fish, and amphibians have evolved natural antifreezes in their blood, proteins that can prevent ice crystals from forming, allowing them to survive temperatures slightly below freezing. Some microscopic organisms, like tardigrades, can enter a state of suspended animation called cryptobiosis, dehydrating themselves and replacing the water in their cells with protective sugars. But these are adaptations for the mild winters of our current world. They offer no defense against a journey to absolute zero. As the temperature continued to fall, past -50, past -100 degrees Celsius, these protective mechanisms would fail. The very molecules of life would become too cold to function. Enzymes, the specialized proteins that catalyze chemical reactions, would become rigid and inactive. The elegant dance of biochemistry that defines being alive would cease. The fundamental process of metabolism, the conversion of nutrients into energy, would stop. Every living thing, from the smallest microbe in the soil to the largest whale in the deep, would succumb. The end would be swift and silent. There would be no struggle, no prolonged period of decline. It would be a sudden, universal cessation of all biological function. The planet's vibrant, complex biosphere would be extinguished, not by fire or cataclysm, but by the simple, inexorable withdrawal of the thermal energy that makes its chemistry possible. While the function of life would cease instantly, the form of life would be preserved with a perfection that is difficult to imagine. The descent into cold would be so rapid and so profound that there would be no time for decay. Decay and decomposition are biological processes, carried out by bacteria and fungi that break down complex organic matter into simpler substances. But these decomposers would be among the first victims of the cold, their own cellular machinery freezing and shutting down. Without them, the process of decay would not happen. As a result, every living organism would be flash frozen, captured perfectly in the last moment of its existence. A bird in mid-flight would be frozen solid, its wings outstretched. A forest of trees would stand as a collection of intricate ice sculptures, every leaf and every needle preserved in perfect detail. Great herds of animals on the plains would be frozen in place, a silent, motionless tableau of life. The oceans, as they froze, would entomb their inhabitants, from schools of fish to the giant squid in the deep, preserving them perfectly within the clear, solid ice. This would be a world transformed into a planetary-scale museum of natural history. Unlike fossils, which preserve only the hard parts of an organism and replace the organic material with minerals over millions of years, this freezing would preserve everything. Soft tissues, skin, fur, feathers, all would remain intact. The colors might fade over cosmic timescales due to radiation, but the physical structure would be perfectly maintained. One could, in theory, walk through this silent world and see a complete and pristine record of the planet's biosphere. You could see the intricate patterns on a butterfly's wings, the expression on a predator's face, the delicate structure of a flower's petals. It would be a snapshot of life, captured at a single, random moment and preserved for eternity. The great dynamic story of life on Earth, with its cycles of birth, growth, death, and decay, would be replaced by a single, static, silent image. The world would become a breathtakingly detailed, but utterly lifeless, sculpture. The beauty of biological form would be separated forever from the process of biological function. This perfect preservation of the macroscopic world invites us to look even deeper, to the preservation of the very instructions for life itself. The perfect preservation of form extends beyond what the eye can see. Locked within every frozen cell of every frozen organism would be the most complex and wondrous molecule known to science: deoxyribonucleic acid, or DNA. DNA is the blueprint of life. It is a long, elegant, double helix molecule that contains the genetic instructions for building and maintaining an organism. This information is encoded in the sequence of 4 chemical bases, a language of life that is passed down from generation to generation. Under normal conditions, DNA is a fragile molecule. It can be damaged by radiation, by chemical reactions, and it begins to break down after an organism dies. Over time, it degrades, making it difficult to recover ancient genetic information from all but the most well-preserved fossils. But on our world at absolute zero, the story is different. With all chemical reactions halted and all thermal motion quenched, the primary agents of DNA decay would be eliminated. The DNA molecule within its frozen cellular vault, would be preserved in a state of near perfection. The entire genetic library of planet Earth would be frozen in time. The complete genomes of every species, from the simplest virus to the most complex mammal, would be held in stasis. The vast, intricate tapestry of genetic information that evolution wove over billions of years would be saved, intact but inert. The subtle variations in DNA from individual to individual, the very basis of heredity and diversity, would also be preserved. It would be the ultimate archive of life's incredible journey. This genetic information would be locked away in the ice and frozen soil, a silent testament to what once was. The potential for life would still be there, encoded in these frozen molecules, but the ability for that potential to be expressed would be gone. The book of life would be complete, its final page written, and it would then be placed in a perfect, frozen library where it could be preserved for all time, but never again be opened or read. This concept of preserving the code of life itself marks a profound moment of finality, leading us to contemplate the end of the very process that created this code in the first place. With all life extinguished and its genetic code locked in a state of perfect frozen preservation, we witness the end of the grandest story our planet has ever told, the story of evolution. Evolution by natural selection is a process of constant change, driven by the interplay of genetic variation and environmental pressure. It is a story of adaptation, of diversification, of life constantly finding new ways to survive and thrive in a changing world. It requires three key ingredients: reproduction, so that traits can be passed on; variation, so that there are different traits to choose from; and selection, where the environment favors certain traits over others. On our frozen Earth, all three of these pillars have been removed. Reproduction is impossible. There is no biological activity, no cell division, no passing of genes to a new generation. Genetic variation is also impossible. DNA is chemically inert, so no new mutations can arise. The genetic library is closed to any new entries. And finally, natural selection is meaningless. There is no environment to select for or against anything. There is no struggle for survival, no competition for resources. There is only a static, unchanging state. The great engine of evolution, which operated continuously on Earth for nearly 4 billion years, would finally and permanently shut down. The story has reached its end. There will be no new species, no new adaptations. The long, branching tree of life, with all its beautiful and complex lineages, will grow no further. Its final state, with all its twigs and branches, is now frozen for eternity. Framing this not as a tragedy, but simply as a conclusion, allows for a peaceful reflection. It is the completion of a narrative. All that could be written has been written. The story of life on Earth, from its simplest single-celled beginnings to its most complex ecosystems, is now a finished work. The cessation of this process, the most creative and dynamic force our world has ever known, marks the true end of biological time. It is the final stillness, not just of individual lives, but of life's collective, ongoing journey. As we bring our consideration of life to a close, we are left with a final, poignant image: the Earth as a silent ark. The story of Noah's Ark is a story of preservation, of carrying a precious cargo of life through a cataclysm to begin anew. Our frozen Earth is also an ark. It carries within it a complete and perfectly preserved record of every species that existed at the moment the cold descended. It is, in a sense, the most complete collection of life imaginable. Every creature, from the familiar to the undiscovered, from the deepest sea trench to the highest mountain peak, is on board this silent vessel. But this arc is different from the one in the ancient stories. Its journey is not toward a new beginning. It sails on a static, endless sea of time. Its destination, a state of perpetual stillness. The passengers within are not sleeping, waiting to be reawakened. They are perfect statues, their life processes permanently halted. The precious cargo of DNA it carries is a library of books that will never be read. This arc tells a complete story, but it tells it to no one. It is a testament to the incredible richness and diversity that the universe, through the patient process of evolution, was able to create in one small, warm corner of the cosmos. The Earth becomes a monument to its own biological history. It is a memorial to the very idea of life. This perspective allows us to see the final state not as one of loss, but as one of ultimate preservation. Nothing more will be created, but nothing that was created will be lost or forgotten. It will all be held safe, locked away from the ravages of time and decay, in the perfect, cold vault of a frozen world. This quiet, contemplative image of a silent, planetary arc concludes our exploration of the fate of life. It provides a sense of peaceful closure and prepares us to take our final step in this journey into the most fundamental and mysterious realm of all, the quantum world, where even in ultimate stillness, a faint motion remains. Our journey has taken us through the freezing of the familiar world, the world governed by the laws of classical physics. But as we approach the absolute floor of temperature, we cross an invisible threshold. We enter a realm where the strange, gentle, and counterintuitive rules of quantum mechanics become dominant. Here, our very understanding of stillness will be redefined. As our Earth cools to just a few degrees above absolute zero, the classical descriptions of physics that have served us so well on our journey begin to break down. In the classical world, we think of particles, like atoms, as tiny billiard balls. We imagine that we could, in principle, know everything about them simultaneously, their exact position and their exact momentum. We also imagine that we could bring them to a complete stop, removing all of their kinetic energy until their momentum is precisely zero. This is the classical vision of absolute zero, a state of perfect and total rest. But the quantum world, the world that governs the behavior of matter and energy at the most fundamental level, tells us a different story. In the early 20th century, scientists like Max Planck, Albert Einstein, Werner Heisenberg, and Erwin Schrödinger discovered that the old rules do not apply in the microscopic realm. Particles are not just particles, they also behave like waves. Their properties are not always definite, but are described by probabilities. And there are fundamental limits to what we can know about them. This transition from a classical to a quantum world is not sudden. It is a gradual shift in dominance. The quantum effects are always present, but at the warm temperatures of our everyday world, they are washed out, hidden beneath the noisy, chaotic motion of thermal energy. As a system becomes colder, and this thermal noise is silenced, the subtle underlying quantum nature of reality begins to emerge and assert itself. The strange behaviors we have already touched upon, like superconductivity and superfluidity, are the first large-scale signs that we have crossed into this new territory. They are macroscopic phenomena that cannot be explained by classical physics at all. They are the collective expression of quantum rules taking over. So, as our Earth settles into its final, coldest state, it becomes a quantum object on a planetary scale. Its properties can no longer be fully understood by thinking of it as a simple, static ball of frozen matter. We must now adopt a new, more subtle perspective, one that embraces uncertainty and the inherent restlessness of the universe, to understand what stillness truly means at absolute zero. This gentle introduction to the quantum realm prepares us to confront one of its most famous and profound principles. At the very heart of the quantum world lies a concept that fundamentally changes our understanding of stillness. Werner Heisenberg's uncertainty principle, formulated in 1927, this principle states that there is a fundamental limit to the precision with which we can know certain pairs of physical properties of a particle simultaneously. The most famous of these pairs is position and momentum. The more precisely you know the position of a particle, the less precisely you can know its momentum, and vice versa. It is not a limitation of our measuring instruments. It is an inherent, inescapable property of the universe itself. The very nature of a particle as both a particle and a wave makes this uncertainty unavoidable. Imagine trying to measure the exact location of a wave in the ocean. A wave is a spread-out disturbance. It doesn't have a single precise location. The same is true for a quantum particle. This principle has a profound implication for our journey to absolute zero. If we were to say that an atom on our frozen Earth has reached a state of perfect rest, we would be claiming to know its momentum with perfect precision. Its momentum would be exactly zero. According to the uncertainty principle, if we know the momentum perfectly, then our uncertainty about the particle's position must become infinite. The particle could be anywhere in the universe. This is clearly not the case. The atoms of our Earth are still, for all intents and purposes, part of the Earth. Therefore, because we know the atoms are located somewhere on our planet, a rough but not infinite knowledge of their position, there must be a corresponding uncertainty in their momentum. Their momentum cannot be exactly and perfectly zero. This means they cannot be perfectly still. There must always be a tiny, residual amount of motion, a fundamental quantum jiggle that can never be eliminated, no matter how cold the system gets. The uncertainty principle forbids a state of absolute, perfect rest. It replaces the classical idea of a static, frozen stillness with a more subtle and dynamic one, a state of minimum possible motion. This leads us directly to the source of this irreducible quantum jiggle. If the uncertainty principle tells us that particles can never be perfectly still, then it must mean they always possess some small, minimum amount of energy. This irreducible, fundamental energy that remains in a system even at absolute zero is called zero-point energy. It is the energy of the quantum ground state. The name comes from the fact that it is the energy that exists at 0 Kelvin. It is the direct consequence of Heisenberg's uncertainty principle. Because a particle confined to a space, like an atom in a crystal lattice, cannot have a definite position, it must have an uncertain momentum, which translates into a minimum amount of kinetic energy. It is the universe's way of saying that nothing can ever be truly and completely locked down. Let us return to our analogy of the atoms in a crystal as tiny spheres connected by springs. In the classical view, at absolute zero, the spheres would be perfectly still. In the quantum view, even at absolute zero, the spheres will continue to vibrate very gently, oscillating around their equilibrium positions. This is not thermal vibration. It is a purely quantum vibration. It is the faintest possible motion, the quietest hum of existence. It is the ground state energy of the quantum harmonic oscillator. This zero-point energy is not just a theoretical curiosity. It has real, observable effects. The most striking example is liquid helium. As we discussed, helium never freezes under normal pressure, no matter how cold it gets. This is because the zero-point vibrations of the helium atoms are so large that they are able to overcome the weak attractive forces that would otherwise bind them together into a solid crystal. The atoms simply jiggle too much to lock into place. Zero-point energy is everywhere. Every particle, every field, Every bit of empty space in the universe possesses this fundamental energy. It is the baseline, the energetic floor upon which the rest of the universe, with all its thermal energy and activity, is built. So, on our Earth at absolute zero, a profound quiet would have descended. The chaotic dance of heat would be over, but it would not be a state of absolute deathly stillness. Instead, the entire planet, every atom within it, would be gently humming with this faint, residual, quantum vibration. It would be a stillness that is, in a subtle way, deeply and fundamentally alive. This is not a violation of our journey toward quietude, but its ultimate fulfillment. It is the discovery that the quietest state is not silence, but a gentle, eternal hum. The concept of zero-point energy extends beyond the atoms of our frozen Earth. It applies to the fabric of space itself. According to quantum field theory, the modern framework for understanding fundamental particles and forces, a vacuum, empty space, is not truly empty. It is a bubbling, seething sea of potential, filled with what are called quantum fields. The zero-point energy we have discussed is the ground state energy of these fields. Even in the coldest, darkest void, these fields are constantly fluctuating. These fluctuations can, for incredibly brief moments, manifest as pairs of virtual particles that pop into existence, exist for a fleeting instant, and then annihilate each other, returning their energy to the vacuum. This process is happening everywhere, all the time. The vacuum of space is a place of immense, latent energy. This underlying energy of the vacuum, the zero-point energy of the quantum fields, connects the state of our frozen Earth to a universal principle. The gentle quantum hum of the atoms in its crystal lattice is a manifestation of the same fundamental energy that permeates the entire cosmos. The Earth, in its final state of stillness, would be in perfect equilibrium with this universal ground state. It would be a quiet island of matter, gently vibrating in tune with the fundamental rhythm of the empty space around it. This perspective elevates our understanding of absolute zero. It is not simply the end of a process of cooling on one planet. It is the attainment of a state of harmony with the foundational energy level of the entire universe. The planet would have shed all of its unique, chaotic thermal energy and settled into the quiet, ordered, and universal energy state of the cosmos itself. It is a state of profound connection, not of isolation. This vision of a world vibrating in tune with the cosmic vacuum leads us to consider one final, strange state of matter that is a beautiful, real-world expression of this quantum coherence. Our journey into the quantum realm at low temperatures would be incomplete without touching upon one of the most remarkable states of matter ever discovered, the Bose-Einstein condensate, or BEC. First predicted by Satyendra Nath Bose and Albert Einstein in the 1920s, and created in a lab for the first time in 1995, a BEC is a state of matter that forms when a gas of certain types of atoms is cooled to temperatures, just a tiny fraction of a degree above absolute zero. At these extreme temperatures, the quantum nature of the atoms takes over completely. The wave-like properties of the atoms, which are usually microscopic, begin to overlap. When the critical temperature is reached, the individual atoms cease to have separate identities. They coalesce into a single quantum object, a superatom, where thousands or even millions of atoms are all in the exact same quantum state, behaving in perfect unison. Creating a BEC is an incredibly delicate process, requiring specific atoms and carefully controlled conditions, so it is not something that would happen to the Earth as a whole. However, it serves as the ultimate real-world example of the quantum coherence we have been exploring. It is the most ordered form of matter known. In a gas, atoms move randomly. In a solid, they are ordered in space, but still have individual vibrations. In a BEC, The atoms lose their individuality entirely and become a single, collective entity, described by a single wave function. It is a beautiful illustration of how, as thermal randomness is removed, the underlying unity of the quantum world can emerge. The BEC is a perfect embodiment of the theme of stillness and order. It represents the ultimate triumph of quantum coherence over thermal chaos. It is a glimpse into the kind of profound simplicity and unity that characterizes the universe at its very lowest energy state, providing us with a tangible, though exotic, touchstone for the abstract concepts we have been contemplating. As our journey through the strange and beautiful landscape of the quantum realm comes to a close, we are left with a new and more profound understanding of stillness. We began this thought experiment with a simple, classical idea of absolute zero, a state of perfect, frozen, and absolute rest. But our exploration of the quantum world has replaced this stark image with one that is far more subtle and, in many ways, more beautiful. We have learned that perfect stillness is forbidden by the laws of nature. The uncertainty principle ensures that there will always be a faint, irreducible motion. This motion is the expression of zero-point energy, the gentle, constant hum of existence that permeates every atom and every inch of space in the universe. It is the quiet, foundational pulse of the cosmos. Therefore, the ultimate state of cold is not one of dead silence, but of a pure, single, harmonious note. It is the end of all chaotic, thermal noise and the revealing of the universe's fundamental tone. Our Earth, at absolute zero, would be a world that has finally shed all of its discord and has settled into this state of perfect quantum harmony. Its atoms would vibrate in unison, not with the energy of heat, but with the energy of the ground state of the universe itself. This redefinition of stillness is the final, pivotal realization of our journey. It transforms absolute zero from a concept of absence and finality into one of presence and fundamentality. It is not an end, but a state of being in its purest form. It is the most profound and peaceful state imaginable, a state of perfect order and quiet, dynamic equilibrium. As we gently release this idea, letting the quantum hum fade into the background, we can carry this sense of peaceful, fundamental quietude with us. Having explored the inner quantum life of our frozen world, we once again lift our gaze to consider its appearance. We have seen how it would become a perfect mirror, reflecting the light of the sun and stars. But now we ask a deeper question. What of its own light? Does it have one? And what becomes of it in the profound cold? To understand a world without light, we must first understand that in a very real sense, every object in the universe is a world with light. Anything that has a temperature above absolute zero emits thermal radiation. This is also known as blackbody radiation. It is the light given off by an object simply because it is warm. The concept can seem counterintuitive because we do not see most objects glowing in the dark. This is because the type of light they emit depends on their temperature. The atoms in any warm object are vibrating, and these vibrating charged particles create electromagnetic waves, light. Colder objects emit lower energy, longer wavelength light, while hotter objects emit higher energy, shorter wavelength light. For example, an object at room temperature, like a book or a table, or even your own body, is constantly emitting light. But this light is in the infrared part of the spectrum, which is invisible to our eyes. We can, however, feel this radiation as warmth, and we can see it with thermal imaging cameras. If you begin to heat an object, like a piece of iron, it will start to glow. First, it will glow a dull red. This is the point at which its black-body radiation has become energetic enough to enter the visible part of the spectrum. As it gets hotter, it will glow orange, then yellow, and then a brilliant white, or even bluish white. The color of the glow is a direct indicator of its temperature. The filament in an incandescent light bulb is a perfect example. It is heated until it is so hot that its black-body radiation is bright white light. The sun, too, is a black-body radiator. Its surface temperature of thousands of degrees determines the yellowish-white light it emits. Our current Earth is also a black-body radiator. With an average surface temperature of about 15 degrees Celsius, or 288 Kelvin, it glows quite brightly in the infrared spectrum. This is the heat that satellites can see from space, allowing them to measure sea surface temperatures and track weather patterns. This faint, invisible glow is the Earth's own light, a constant signal of its thermal life. Understanding this universal principle is the key to seeing what happens when that thermal life is extinguished. Equipped with the understanding that all warm objects glow, we can now turn back to our Earth on its journey to absolute zero. As the planet cools, its black-body radiation will change in two ways. First, the intensity of the radiation will decrease dramatically. The amount of energy an object radiates is proportional to its temperature to the fourth power. This means that even a small decrease in temperature leads to a very large decrease in radiated energy. As the Earth cools from its current temperature down into the deep cryogenic range, the amount of infrared light it emits will plummet. Its thermal glow, which is already invisible to us, would become fainter and fainter, detectable only by the most sensitive instruments. Second, the peak wavelength of the radiation will shift. As the Earth cools, the light it emits will move from the infrared to even longer wavelengths, microwaves, and then radio waves. The planet's thermal color would be shifting far beyond the visible spectrum. As the temperature continues its relentless descent, approaching the final few degrees above zero, the emitted radiation would become incredibly faint, its wavelength stretched to be miles long. The Earth would be whispering its thermal state to the universe in the form of the lowest energy radio waves imaginable. And then, at the theoretical moment of reaching absolute zero, this final whisper would cease. An object at zero. Kelvin emits no thermal radiation whatsoever. Its black-body spectrum is completely dark. The planet's own light would be extinguished. The constant, faint broadcast of its thermal state into the cosmos would finally go silent. This is a profound kind of invisibility. While the planet would still be visible in the conventional sense, we could see it by the sunlight it reflects. It would become completely invisible in the thermal sense. Any alien civilization with an infrared telescope would see our vibrant, warm planet slowly fade to black, disappearing from their thermal view of the solar system. The Earth would have ceased to radiate its own energy, its own light. It would become a purely passive object, only visible by the light of others. This vanishing of its thermal signature is a key step in its final transformation, leading us to a more precise understanding of what it means to be truly thermally dark. The term black-body radiation can be a little confusing. It comes from the concept of an idealized object called a black body, which is defined as a perfect absorber and emitter of radiation. A perfect black body absorbs 100% of the radiation that strikes it, reflecting none. Because it reflects no light, it would appear perfectly black if it were cold. When you heat a black body, the light it gives off is due only to its temperature, not to any reflected light. While no real object is a perfect black body, the concept is a powerful tool in physics. On our journey, we have established that our frozen Earth has become a perfect mirror, reflecting almost all light. This makes it the opposite of a good absorber. However, when we speak of it becoming perfectly black, we are referring to its properties as an emitter. At absolute zero, the Earth emits no thermal radiation. In the thermal spectrum, it is a perfect black. If you were to look at the solar system with a camera that could only see thermal infrared light, all the warm objects, the sun, the planets, the asteroids, would be glowing. But the Earth at absolute zero would be a patch of perfect, featureless blackness. It would be an absence on the thermal map, a void. This distinguishes it from the simple color black. A piece of black cloth appears black because it absorbs most of the visible light that hits it, but it is still at room temperature, so it is glowing brightly in the infrared. Our frozen Earth, by contrast, does not glow in any part of the spectrum. It is truly, fundamentally dark. Its darkness is not a property of its surface material's color, but a property of its ultimate thermal state. It is the darkness of zero energy emission. This state of being thermally black, while being visually a perfect mirror, is a fascinating duality. The planet would be simultaneously one of the brightest objects in the solar system to the naked eye, and one of the darkest, most invisible objects to a thermal sensor. It would be a world of complete contrasts, visually brilliant, thermally black. This dual nature paints a more complete picture of our world's final state, a serene object of stark and simple extremes, leading us to a final, poetic image of its new presence in the cosmos. With our world now understood as a brilliant mirror in visible light and a patch of perfect blackness in thermal light, we can imagine its new presence as it continues its orbit through the solar system. It has become a kind of shadow, not a shadow in the sense of blocking light. It reflects light brilliantly, but a shadow in the thermal sense, a moving void on the infrared backdrop of the cosmos. As it passes in front of more distant, warmer objects, like the faint glow of interstellar dust clouds or the distant planets, it would create a perfect occultation, a black disk moving across a faintly glowing background. Its passage would be marked by the temporary snuffing out of the faint warmth behind it. It would be a cold shadow, its presence felt not by what it adds, but by what it takes away from the thermal view. This idea of a shadow creates a serene, almost ghostly, image of the planet. It is physically present, its gravity still tugging on the moon and the other planets, its mirrored surface still reflecting the sun. But its thermal presence, the signature of its once active inner life, is gone. It has become a passive player on the cosmic stage, its most notable feature being its profound and absolute coldness. It is a quiet wanderer, a silent sphere defined more by its absence of energy than by any active property. This poetic framing of the Earth as a thermal shadow provides a gentle sense of closure to our exploration of its light. It summarizes its new, dual nature, visually bright, thermally dark, in a single, peaceful image. It is an object of serene simplicity, a perfect black circle on the faint, warm canvas of the universe, a quiet testament to the state of zero emission. As we conclude this chapter on our world without its own light, let us return to the duality that defines it. It is a world that has ceased to speak, but has become a perfect listener. Its own voice, its thermal radiation, has fallen silent, but its surface, a near-perfect mirror, now reflects the voices of everything else in the cosmos with unparalleled clarity. This is its final, peaceful state. It has traded its internal active life for a passive, reflective one. It no longer tells its own story of warmth and geology through its infrared glow. Instead, it reflects the grand, silent story of the universe around it. the light from the most distant quasars, galaxies that existed billions of years ago, will travel across the void and find its final destination as a faint reflection on the surface of our frozen world. The entire celestial sphere, the history of the universe written in light, would be mirrored on its face. This is not a state of emptiness, but a state of pure receptivity. The Earth has become a perfect canvas. Its own complex, colorful painting has been erased, allowing the masterpiece of the cosmos to be reflected in its place. This balance between its internal blackness and its external brilliance is the final truth of its appearance. It is a world of sublime and simple contrast. This serene image of a world that has become a dark yet shimmering mirror for the stars provides a peaceful endpoint for this stage of our journey. We have defined its final form, both inside and out. It is a world of quantum humming, perfect crystals, and silent reflection. We can now turn to the final, fundamental question of our journey. How could such a state ever be reached? We must now gently confront the ultimate law that governs this entire process. We have journeyed far in our thought experiment, imagining a world transformed by a descent into absolute cold. We have explored its effects on every aspect of the planet. But now, we must turn to a fundamental law of the universe that governs this entire process, a law that tells us our destination is, in reality, unreachable. Our entire journey has been guided by the principles of thermodynamics, the science of heat and energy. The first law speaks of the conservation of energy. The second law speaks of the inevitable increase of entropy, or disorder, in the universe. But it is the third law of thermodynamics that speaks directly to our destination. Formulated in the early 20th century, primarily by the chemist Walter Nernst, the third law can be stated in a simple way. It is impossible to reach absolute zero through any finite number of steps. This law is not an observation about technological limitations. It is a fundamental principle woven into the fabric of the universe, much like the speed of light being an unbreakable cosmic speed limit. The law arises from the very nature of heat and entropy at low temperatures. As a system gets colder, its entropy, its internal disorder, decreases. The third law states that as the temperature approaches absolute zero, the entropy of the system approaches a minimum value. For a perfect crystal, this minimum value is zero. The consequence of this is profound. To cool something, you need to perform a process that removes entropy from it. Think of a refrigerator. It uses a cycle of compressing and expanding a fluid to pump heat and thus entropy out of its interior and dump it into the room outside. The problem is, as the object you are cooling gets closer and closer to absolute zero, its entropy gets smaller and smaller. There is less and less disorder left to remove. The process of removing that last little bit of entropy becomes exponentially more difficult. Each step you take, each unit of heat you manage to extract, lowers the temperature by a smaller and smaller amount. You can get incredibly close. Laboratories on Earth have achieved temperatures of just fractions of a billionth of a degree above absolute zero. But you can never take that final, infinite step to reach the 0 point itself. The third law, therefore, transforms our journey. It reveals that absolute zero is not a destination one can arrive at, but rather a theoretical limit, a horizon that one can approach forever but never touch. Our thought experiment, then, has been the exploration of this impossible limit. It has been a gentle journey toward a state of perfection that the universe allows us to glimpse, but not to fully attain. Let us try to visualize the third law of thermodynamics with a gentle metaphor. Imagine you are walking toward a wall. With each step you take, you cover half the remaining distance to the wall. Your first step takes you halfway there. Your second step takes you another quarter of the way, halfway through the remaining half. Your third step takes you an eighth of the way. You are always getting closer to the wall, but you never actually reach it, because there is always another, smaller, half the distance to cover. You can get so close that the space between you and the wall is thinner than a piece of paper, thinner than an atom, but you can never take the final step that lands you at the wall itself. The journey to absolute zero is like this. It is a journey of an infinite number of smaller and smaller steps. Each cooling cycle, each process designed to remove heat, takes you a little bit closer, but the amount of progress you make gets smaller and smaller with each step. This is because, as a substance gets colder, it has less energy to give up. It becomes harder and harder to coax the last vestiges of thermal vibration out of the atoms. The very processes of cooling rely on interacting with the substance, and at these low temperatures, the substance barely interacts at all. It is like trying to have a conversation with someone who will only whisper, and whose whispers are getting progressively quieter. Eventually, you can no longer hear them at all. The universe, in its deep wisdom, has made the state of perfect stillness infinitely elusive. We can approach it. We can get to 99.999% of the way there. But we cannot cross the finish line. This realization adds a layer of serene beauty to our thought experiment. We have been exploring a perfect ideal. We have been imagining what it would be like to stand at the wall, even if we can never truly get there. It makes the state of absolute zero even more special, a sacred ground of physics that can be approached but never entered. It is the ultimate limit, the final, quiet horizon. Even if the third law of thermodynamics did not forbid us from reaching absolute zero, there is another, more practical obstacle woven into the fabric of the cosmos itself. The universe is not perfectly cold. Even in the deepest, darkest voids of intergalactic space, far from any star, there is a faint, residual warmth. This warmth is the afterglow of the Big Bang. It is called the cosmic microwave background, or CMB. When the universe was very young, it was incredibly hot and dense, filled with a searing plasma. As the universe expanded and cooled, this plasma eventually thinned out, enough for light to travel freely. The light from that moment, the universe's first light, has been traveling through space ever since. And as space has expanded over 13.8 billion years, the wavelength of this light has been stretched out, from high-energy gamma rays into the microwave part of the spectrum. Today, this ancient light fills the entire universe. It is a perfect blackbody radiator with a temperature of about 2.7 Kelvin. This means that even in the emptiest space imaginable, the baseline temperature is 2.7 degrees above absolute zero. This cosmic microwave background acts as a universal, gentle heat bath. Any object left alone in the void will eventually cool down until it reaches equilibrium with the CMB. It will absorb as much microwave radiation as it emits, and its temperature will stabilize at 2.7 Kelvin. It can get no colder on its own, because the universe itself is always bathing it in this faint, ancient warmth. So, for our Earth to ever reach absolute zero, it would not only have to overcome the infinite challenge of the third law, but it would also have to be completely isolated from the rest of the universe, shielded from the gentle, persistent glow of creation's dawn. This further reinforces the impossibility of our journey, framing it even more clearly as a pure, idealized thought experiment. To continue our pure thought experiment, to follow our path all the way to its theoretical end, we must make one final, imaginary leap. We must conceptually isolate our planet from the rest of the universe. Let us imagine, just for the sake of our journey, that we can construct a vast, perfect shield around the Earth. This shield would be a perfect insulator, allowing no heat to pass through it, and it would be a perfect reflector, turning away every single photon of the cosmic microwave background. It would seal our planet off in its own private pocket universe, where the only energy present is the energy contained within the Earth itself. Inside this theoretical cocoon, the faint 2.7 Kelvin warmth of the universe could not enter. The Earth would now be truly alone with its own energy, free to radiate it away into the perfect cold of the shielded space around it, without any interference. This act of imagining a perfect shield allows us to bypass the obstacle of the cosmic microwave background and continue our journey down the final few degrees. It is a necessary step in our idealization, allowing us to focus solely on the internal processes of cooling and the ultimate limits imposed by the third law. It underscores that our exploration is not one of practical possibility, but of theoretical purity. We are not asking what would happen, but what would it be like if it could happen. By placing our Earth within this imaginary vessel of perfect isolation, we give ourselves permission to walk those final, infinite steps toward the wall, to explore the very last moments of the slow surrender of energy, and to contemplate the removal of the very last quantum of heat. Within our perfectly shielded Earth, the journey continues into the realm of the ultra-low temperatures, the microkelvins and the nanokelvins. At this stage, the very concept of heat changes. We are no longer talking about the bulk properties of a substance, but the energy states of individual atoms. Heat energy is quantized, meaning it exists in discrete packets or quanta. For the vibrations in a crystal lattice, these quanta are called phonons. A phonon is a quantum of vibrational energy, just as a photon is a quantum of light. Cooling a crystal at this level is the act of removing these phonons one by one. As our Earth cools down its final fraction of a degree, it is slowly being drained of its remaining phonons. The crystal lattices are becoming quieter and quieter, their vibrations being damped out, quantum by quantum. This process is incredibly delicate. The energies involved are minuscule, and the phonons are very difficult to remove. The techniques used in laboratories to achieve these temperatures are complex, often involving lasers and magnetic fields to trap atoms and gently coax them into their lowest energy states. On our planetary scale, this would be the final, slowest stage of cooling. The planet would be radiating away its last few quanta of vibrational energy in the form of incredibly low-energy photons. The process would slow down exponentially as it approached zero. The removal of the very last phonon from a crystal is a task that would require an infinite amount of time, a perfect illustration of the third law in action. This poetic image of a planet shedding its last units of vibrational energy, one quantum at a time, is the ultimate expression of the slow surrender. It is a majestic, silent, and infinitely long process, the final, gentle exhale of a world settling into its ground state, a state of perfect and simple order. Our infinite journey downward concludes, at least conceptually, at a state of perfect order. As we have discussed, this is the realm of entropy. The second law of thermodynamics tells us that the entropy of the universe as a whole always tends to increase. This is why heat flows from hot to cold, and why ordered systems tend to become disordered over time. It is the arrow of time, the relentless march toward chaos. But the third law provides a counterbalance. It tells us that there is an anchor point for entropy, a baseline of perfect order. At absolute zero, the entropy of a perfect system is zero. It is the one point in the universe where the relentless pressure toward disorder is completely balanced. It is a state of perfect information. In a high-entropy system, like a gas, there is a lot of missing information. The atoms could be arranged in any one of a huge number of random configurations. In a perfect crystal at absolute zero, there is only one possible configuration. The position of every atom is known. There is no randomness, no missing information. It is a state of ultimate simplicity. Our hypothetical Earth, upon reaching this state, would become a planet of zero entropy. It would be a perfectly ordered object. This is the ultimate expression of the stillness and quietude we have been seeking. It is not just a physical stillness of motion, but a statistical stillness of configuration. No further change is possible because the system is already in its most perfect, most ordered state. This connection to entropy, one of the deepest and most powerful concepts in all of physics, provides a final, profound layer to our journey. The descent into cold is a descent into order. It is a journey against the normal flow of time, away from chaos and toward simplicity. The state of absolute zero is the ultimate sanctuary from the second law, a place of perfect peace and timeless, unchanging order. It is the gentle end of a very long thought. Having explored the physics of a world at absolute zero and the impossible journey to get there, we now shift our perspective one last time. In this final, static state, what remains? What story would this frozen, silent sphere tell? We now explore the Earth as a perfect, unchanging monument to its own past. If our world were to be frozen in an instant, it would become a perfect snapshot of a moment in time. But it would be more than that. It would preserve not just the state of things at the final moment, but also the accumulated history written upon its surface. The grand structures of civilization, the products of centuries of human endeavor, would be frozen in place. Cities would stand as silent, crystalline memorials. Their skyscrapers, bridges, and homes would be perfectly preserved, first under a layer of frozen air, then perhaps buried in the slow drift of other cosmic dust over eons. The materials would be incredibly brittle, but in the absence of wind, water, or seismic activity, there would be nothing to disturb them. They would simply remain. The great monuments of human history, the pyramids of Giza, the Great Wall of China, the stone circles of Stonehenge, would be locked into the frozen ground. These structures, which have already weathered thousands of years, would find their slow erosion halted completely. They would become eternal records, their stones no longer subject to the patient wear of time. Roads, railways, and canals would trace the paths of commerce and connection across the continents, a permanent map of how our civilization was organized. Even the smaller, more ephemeral signs of life would be preserved. A footprint in what was once soft mud would be frozen solid, a perfect record of a single step taken at the last moment. A book left open on a table would remain open to that page forever, its text preserved and readable, though its paper would be as fragile as a wafer of ice. The planet would become a vast and detailed archaeological site, containing the complete and undisturbed record of an entire civilization. Every layer of history, from the most ancient ruins to the most modern cities, would be held in perfect stasis. It would be a silent, comprehensive story of humanity's journey, its triumphs, its follies, and its final, quiet moment, all written in stone and steel and ice. Let us delve deeper into this idea of the frozen earth as an archive. It would be more than just a collection of large structures. It would be a library containing every physical object ever created by humanity, preserved in its final resting place. Every museum in the world would be perfectly preserved, its artifacts held in a state of arrested decay. The paintings in the Louvre, the sculptures in the Vatican, the historical documents in the world's national archives, all would be safe from the ravages of time. The delicate pigments in a Renaissance painting would no longer be subject to fading. The ancient parchment of a medieval manuscript would no longer grow brittle with age. The information they contain would be preserved for eternity. Our libraries, filled with the collective knowledge, stories, and dreams of our species, would become silent, frozen stacks. The books themselves would be unreadable in a conventional sense, their pages frozen solid. But the information would still be there, encoded in the ink on the page, waiting for any hypothetical future observer with the means to access it. The same would be true for our digital information. The servers that hold the internet, the hard drives in our homes, the silicon chips in our phones, all would be frozen. At temperatures near absolute zero, there would be no electrical activity, but the physical patterns that encode the data, the magnetic orientations on a platter, the trapped electrons in a flash drive, could be preserved indefinitely. The entire digital footprint of our civilization, from the most profound scientific data to the most trivial social media post, would be locked away in this frozen electronic vault. It would be a complete and unfiltered record of our thoughts, our communications, and our culture in the 21st century. Every home would be its own miniature museum, a perfect diorama of daily life, its contents preserved exactly as they were left. This planetary library would be staggeringly complete. It would contain not just the curated, important artifacts we place in museums, but everything. A child's drawing, a half-finished cup of coffee, a simple wooden chair. Each would be preserved with the same fidelity as a royal crown. It is the ultimate democratic archive, where every object, no matter how mundane, is given the same status of eternal preservation. The earth becomes a testament not just to our grand achievements, but to the simple, everyday texture of our lives. The memory of our planet, preserved in the absolute cold, would extend far deeper than the history of humanity. The rocks themselves are a library, and their pages tell a story that is billions of years old. The fossil record, the chronicle of life's long journey on Earth, would be perfectly preserved within the frozen crust. The delicate bones of the dinosaurs, the intricate shells of ancient sea creatures, the faint imprints of the first multicellular life, all would be held in a state of perfect stasis. The slow geological processes that can damage or destroy fossils, erosion, metamorphosis, subduction, would have all ceased. The fossil record, which is already a precious and incomplete window into the past, would be protected from any further degradation. The information it contains, which paleontologists have so patiently worked to uncover, would be safe. But it would be more than just the fossils. The rocks themselves tell a story. The layers of sedimentary rock are a timeline, each layer representing an epoch of history. The chemical composition of those layers tells us about the atmosphere and climate of the ancient Earth. The alignment of magnetic minerals in volcanic rock tells us about the past behavior of the planet's magnetic field. All of this geological data, the planet's autobiography written in stone, would be frozen and preserved. The great geological features of the world, the Grand Canyon, the Himalayan mountains, the Great Barrier Reef, are themselves historical documents. They tell stories of erosion, tectonic collision, and biological growth over millions of years. On our frozen Earth, these stories would be captured at their final chapter. The great processes that wrote them, now finished. The Earth would become a complete geological archive, preserving not just the history of life, but the history of the planet itself, its deep, slow rhythms of change, now silent and still. This deep memory, written in rock and bone, would be the final, underlying text in our planetary library. Beyond the rock, another, more delicate archive would also be perfectly preserved. The great ice sheets of Antarctica and Greenland, and the new, global shell of frozen ocean and atmosphere. These bodies of ice are their own unique form of time capsule. As snow falls and compacts into ice, it traps tiny bubbles of the surrounding air. By drilling deep ice cores, scientists can analyze these ancient air bubbles and directly measure the composition of Earth's atmosphere from hundreds of thousands of years ago. They can track the rise and fall of carbon dioxide and other greenhouse gases through past ice ages. On our frozen world, this incredible record would be sealed and preserved. The ancient atmospheres trapped in the Antarctic ice would remain, and the new top layer of frozen atmosphere would serve as a perfect, complete sample of the air at the very final moment. The ice also traps other things, like layers of volcanic ash from great eruptions, which allow scientists to date the layers of the core with great precision. It traps cosmic dust, giving us a record of the material falling on our planet from space. It even traps pollen, telling us what kinds of plants were growing nearby in the distant past. This entire, multi-layered, high-fidelity record of the planet's recent climate and atmospheric history would be preserved indefinitely. The frozen oceans, too, would hold their own secrets. The chemical composition of the water, the remains of deep-sea organisms, the sediments on the ocean floor, all would be locked in place. The planet becomes a series of nested archives, from the deep rock to the frozen seas to the ancient ice, and finally to the newly frozen sky, each layer holding its own unique and irreplaceable story of the world that was. As we conclude our reflection on the preserved memory of our planet, we arrive at a gentle, philosophical quietude. We have imagined a world that has become the perfect archive, a complete and flawless record of its own physical, biological, and cultural history. Every fossil, every artifact, every line of genetic code, every book, every digital file is preserved in a state of eternal, unchanging stasis. It is a story of incredible richness and detail, a story of a world that was once vibrant with change, complexity, and life. But we are left with a quiet, profound thought. This is a story told to no one. The civilization that created the cities and the libraries is now part of the exhibit. The living beings whose history is written in the fossils and the DNA are now silent statues. There are no readers left. The Earth, in its final state, becomes a work of art with no audience. It is a library with no patrons. It is a memory that exists only for itself. This does not diminish the value or the beauty of what is preserved. A beautiful object is still beautiful, even if no one is there to see it. A profound story is still profound, even if no one is there to hear it. The frozen Earth would simply exist, a silent testament to the incredible journey it once undertook. Its value would no longer be in its utility or its meaning to an observer, but simply in its being. It is a quiet, meditative thought. It invites us to consider the nature of memory and meaning. Does a story need a listener to have power? Does a world need an inhabitant to have significance? On our frozen, silent ark, the answer is a quiet, unspoken one. The story is enough, in and of itself. Having explored the rich, preserved memory within our frozen planet, we now pull our perspective away once more. We travel far out, beyond our solar system, to view this entire thought experiment from a vast, cosmic distance. From this vantage point, the story of our world finds its place within a much grander narrative. From the perspective of our own galaxy, the Milky Way, the Earth is an almost infinitesimally small object. It is one of 8 planets, orbiting one of at least 200 billion stars. Our galaxy, in turn, is one of hundreds of billions of galaxies in the observable universe. From this vast, cosmic viewpoint, the dramatic and profound transformation we have spent our entire journey exploring would be a quiet and almost unnoticeable event. An astronomer in the Andromeda galaxy, looking at our sun, would have no way of knowing what had happened. The sun would appear as a single, unresolved point of light, and its planets would be completely invisible. The freezing of the Earth, the silencing of its biosphere, the fracturing of its continents, all of this would be a local affair, a silent, private moment in one tiny corner of the cosmos. This perspective is not meant to diminish the significance of our world, but rather to place it in a context of serene humility. It reminds us that the universe is vast, ancient, and filled with processes that dwarf our own experiences. The laws of physics that would govern the freezing of our world are the same laws that govern the formation of stars, the collision of galaxies, and the expansion of the universe itself. Our planet's hypothetical story is just one quiet verse in an epic poem of cosmic evolution. This viewpoint invites a sense of peace. The universe is not centered on us. It is a grand, interconnected system, and our world is just one small part of it. The end of our planet's warmth and life, in this context, is not a cosmic tragedy, but simply a transition, a small system coming to equilibrium according to the universal rules. It is a quiet settling, a tiny speck of dust finding its final, peaceful resting place in a vast and silent cathedral. From this distant, cosmic perspective, we can appreciate that everything that happened in our thought experiment was simply an expression of the unchanging laws of physics. The principles of thermodynamics, of quantum mechanics, of gravity, and of electromagnetism are believed to be universal. They work the same way in the most distant galaxies as they do in our solar system. The journey of our Earth to absolute zero was not a unique or special event, but a predictable outcome given the initial, hypothetical condition of removing its source of heat. Any rocky planet of similar size and composition anywhere in the universe would undergo a similar transformation if placed in the same circumstances. Its atmosphere would freeze, its oceans would solidify, its crust would fracture, and its matter would take on the strange properties of the ultra-cold. There is a profound sense of peace to be found in this universality. It means that the universe is not chaotic or arbitrary, but is governed by a deep and elegant order. The same rules apply everywhere, to everyone, and to everything. Our planet's story, in this light, is not a story of something being broken, but of something conforming perfectly to the grand design. It is a story of a system following its natural path toward its lowest energy state, a path laid out for it by the fundamental constants and principles of the cosmos. This removes any sense of judgment or emotion from the event. It is not good or bad. It simply is. It is physics. The transformation of our vibrant, living world into a silent, crystalline sphere is a beautiful, if stark, demonstration of the power and inevitability of these universal laws. It is a quiet affirmation that we are part of a coherent, predictable, and ordered cosmos. Looking out from our cosmic vantage point at the sea of stars in our galaxy, we are reminded of the incredible diversity of worlds that likely exist. Since the 1990s, astronomers have discovered thousands of exoplanets, planets orbiting other stars. Statistical estimates based on these discoveries suggest that there are billions of planets in the Milky Way alone. These worlds come in a staggering variety. There are gas giants larger than Jupiter, orbiting closer to their stars than Mercury. There are super-Earths, rocky worlds larger than our own. There are planets that orbit two stars at once, and there are likely rogue planets wandering through interstellar space alone, without a star to warm them. Each of these worlds has its own unique story, its own unique fate. Some are searingly hot, their surfaces molten rock. Others are perpetually frozen, having formed far from their star's warmth. Some may be water worlds, completely covered by a global ocean, and a precious few, in the habitable zone around their star, might be like our Earth, with the potential for liquid water and life. Our hypothetical story of an Earth frozen to absolute zero is just one possible narrative out of countless billions. While we have explored the end of warmth on our world, on another world, a young planet might just be warming up, its volcanoes releasing the gases that will form its first atmosphere. While our world's life is being extinguished, on another, the first simple cells might be stirring in a primordial ocean. The universe is a vast tapestry of these stories, all unfolding simultaneously. Placing our own world's story within this grand cosmic context helps to soften any sense of loss. Our planet's fate is not the only story. It is part of a much larger, ongoing narrative of planetary evolution with infinite variations and possibilities. The cosmos is a place of endings, yes, but it is also and always a place of beginnings. The end of one story is simply the backdrop against which countless other stories are being told. The cosmic perspective is not just one of space, but also of time. The timescales of the universe are so immense that they are difficult for the human mind to grasp. Our planet is 4.5 billion years old. Our species is only a few 100,000 years old, but the universe will go on for trillions upon trillions of years. In this deep, future time, our frozen Earth would continue its silent journey. It would orbit the Sun, a faithful, crystalline companion. Over billions of years, its orbit, like all orbits, might slowly change due to the subtle gravitational tugs of other planets. Over even longer timescales, it would be subjected to a slow, gentle rain of micrometeorites and cosmic dust, which would gradually bury its mirrored surface under a thin, dark blanket. It would witness the slow, majestic evolution of the rest of the solar system. It would see the other planets continue their stately dance. But its most significant companion would be the Sun. The Sun is a middle-aged star. In about 5 billion years, it will exhaust the hydrogen fuel in its core and begin to die. It will swell into a red giant, its outer layers expanding to engulf the orbits of Mercury, Venus, and possibly the Earth itself. If our frozen Earth is not consumed, it will be scorched by the intense heat of the dying Sun, its frozen layers of atmosphere and ocean boiled away into space. Then, after the red giant phase, the Sun will shed its outer layers and collapse into a white dwarf, a dense, Earth-sized remnant that will slowly cool and fade over trillions of years. Our planet, or what remains of it, would then continue its journey in the faint light of this stellar ghost, a silent wanderer in a dying solar system. This long, patient view of the future places our entire thought experiment in an even larger context, as just one chapter in a much longer, more cosmic story. Looking even further into the deep future, beyond the death of our own Sun, we see a universe that is itself growing older and colder. The era we live in, the stelliferous era, is the age of stars. It is a bright, energetic, and active time in cosmic history, but it will not last forever. Star formation, the process of great clouds of gas collapsing to form new stars, is already slowing down. The gas is being used up. One by one, over trillions of years, the stars will burn through their fuel and die. The massive stars will have long since exploded as supernovae. The smaller, long-lived red dwarf stars will be the last to go, eventually fading into black dwarfs, cold, dead embers of what were once stars. The universe will become a much darker and quieter place. The galaxies themselves will dissolve, their dead stars slowly being ejected by gravitational interactions, wandering alone through the expanding void. The universe will be populated by these stellar remnants, along with neutron stars and black holes. The age of light and warmth will be over. The cosmos will enter a long, slow, degenerate era, a universe of darkness and immense, quiet timescales. This vision of the far, far future provides the ultimate context for our journey. The freezing of our Earth is, in a sense, a small, premature preview of the fate that awaits all matter in the universe. The principles of thermodynamics that governed our planet's cooling are the same principles that will govern the cooling of the entire cosmos. This leads us to the final, grandest connection of our journey, the theoretical concept of the heat death of the universe. This is one possible ultimate fate for our cosmos, a direct extrapolation of the second law of thermodynamics. It posits that over an unimaginable timescale, the entire universe will eventually reach a state of maximum entropy. All the available energy will have been evenly distributed. All the temperature differences that drive work and change will have been smoothed out. The universe will have reached a state of perfect thermodynamic equilibrium at a temperature just fractions of a degree above absolute zero. There will be no more stars, no more gradients, no more change. The universe itself will have grown cold and dark and still. In this context, our story of the Earth reaching absolute zero is a microcosm of the universe's own potential destiny. Our planet's journey from a warm, dynamic, and complex system to a cold, static, and simple one is the same journey that the entire cosmos may one day take. The Earth, in our thought experiment, simply got there early. This final perspective is one of ultimate peace and unity. It connects the fate of our tiny, individual world to the ultimate fate of everything. It suggests that the state of cold, quiet, simple equilibrium is the natural, final resting place for all things. It is not an end in the sense of a failure, but in the sense of a completion. The universe will have told all its stories, used all its energy, and will finally settle into a state of profound and eternal rest. Our small, crystalline planet becomes a symbol of that ultimate peace, a quiet harbinger of the final stillness to come. We have journeyed to the theoretical, impossible end. We have explored a world of perfect stillness and order. Now, to conclude our exploration, let us engage in one final, gentle act of imagination. Let us consider the reverse. What if, after an eternity in the cold, a source of warmth were to return? Our entire journey has been a process of removing energy. We have followed the slow, inexorable drain of heat from our world until it reached its ground state. Now, let us imagine the opposite, the slow, gentle reintroduction of energy. This is, of course, as impossible as the original journey. We are in the realm of pure thought experiment, a gentle reversal of the film to better understand what we have seen. Let us imagine a new, benevolent star, a source of warmth, is brought near our frozen Earth. Or perhaps some unknown, futuristic technology allows us to slowly and carefully bathe the planet in energy. The process would have to be incredibly slow. The frozen Earth is a world of extreme brittleness. A sudden application of heat would create massive thermal shocks, shattering the planet even more completely. The return of warmth would need to be as patient and as stately as its departure. We begin by adding the first quantum of energy. A single photon is absorbed, its energy transforming into a single phonon, a tiny quantum of vibration in the crystal lattice. The process of reawakening begins at the most fundamental level. One by one, the atoms of the frozen world would be nudged out of their zero-point hum into slightly more energetic vibrations. The entropy of the planet, which was at or near zero, would begin to increase. The perfect order would be disturbed by the first whispers of new motion. The process would be a perfect reversal of the third law. The first few units of energy would cause the largest jump in temperature, as the heat capacity of the materials is so low at these temperatures. The journey upward from absolute zero would begin with a rapid initial climb, which would then slow as the planet became warmer and more able to absorb energy. This reversal is a gentle way to begin thinking about the immense inertia of the frozen state. It is a world locked in perfect stability, and the energy required to undo that state is as monumental as the energy that was lost to create it. It is the beginning of a slow, planetary-scale thaw. As we continue to gently add energy to our frozen world, the first stirrings of change would be microscopic, deep within the crystalline structure of matter. The quiet, coherent hum of zero-point energy would slowly be augmented by the chaotic, incoherent vibrations of thermal energy. The atoms, once locked in their most perfect, ordered positions in the crystal lattice, would begin to oscillate more widely. The perfect crystal would begin to acquire imperfections. This reintroduction of thermal motion would begin to undo the strange quantum phenomena that dominated the cold. As the temperature rose past a few Kelvin, the superconductivity of the planet's metallic elements would vanish. The materials would regain their electrical resistance. The persistent, frictionless currents flowing through the planet's crust would encounter friction once more, and they would quickly dissipate their energy as heat, contributing to the warming process. The planet would lose its ability to perfectly expel magnetic fields. The properties of all materials would begin to shift back toward their more familiar states. They would gradually lose their extreme brittleness and regain some of their ductility. The very color and thermal properties of the surface would begin to change. The process would be a slow, patient reawakening of the dynamic properties of matter. For a very long time, nothing would be visible on a large scale. The planet would still appear to be a solid, frozen sphere. But deep within, at the atomic level, the great stillness would be ending. The dance of heat would be starting again, a slow and quiet crescendo, building from the quietest possible note. This is the process of reintroducing disorder. The entropy of the world would be increasing, and the arrow of time, which had seemed to stop, would begin to move forward again. These first, invisible stirrings are a crucial part of the process. The planet is not just being warmed, it is being re-randomized. The perfect simplicity of its frozen state is giving way, atom by atom, to the complex, chaotic motion that characterizes a warm world. It is the necessary preparation for the grand, macroscopic changes that are to come. After a long period of slow, internal warming, the temperature of the planet would eventually reach the melting and sublimation points of the substances on its surface. The great thaw would begin. The first layer to respond would be the topmost shell of frozen atmosphere. As it warmed, the solid nitrogen and oxygen would not melt into a liquid, but would sublimate, turning directly into a gas. A new, thin atmosphere would begin to form around the planet. Slowly, over millennia, the entire frozen sky would evaporate from the surface, returning to its gaseous state. The atmospheric pressure would begin to rise. With the return of an atmosphere, sound would once again be possible. The silence would be broken, first by the faint whisper of a nascent wind, driven by the first small temperature differences on the warming surface. Next, as the temperature continued to rise, the great global sheet of water ice would begin to melt. The process would start at the surface, forming vast meltwater pools and lakes on top of the ice. These pools would absorb more sunlight than the surrounding ice, accelerating the melting. Great rivers would begin to carve channels into the ice sheet, and immense, planetary-scale waterfalls would cascade into newly forming seas. The return of liquid water would be the most significant step in the planet's reawakening. The oceans would slowly begin to fill again. The water cycle, which had been dormant for eons, would restart. Clouds would form in the new atmosphere, and for the first time in an age, rain would fall. The world would begin to wash itself clean, the brilliant white of the ice giving way to the deep blue of liquid water and the dark brown of the revealed continents. The familiar face of our pale blue dot would, slowly and majestically, re-emerge from its crystalline shell. As the world thawed and the ice receded, it would reveal a landscape that was profoundly and permanently changed. The planet would not simply return to the way it was before. It would bear the scars of its time in the deep cold. The most dramatic of these scars would be the immense network of canyons and fissures created by thermal contraction during the great shattering of the continents. These vast chasms, miles deep and hundreds of miles wide, would now be permanent features of the Earth's topography. They would dwarf any canyons that exist on our world today. As the oceans filled, some of these great fissures would become deep, narrow sea channels, creating new and intricate coastlines. On land, they would become immense, sheer walled valleys. The surface of the rock itself would be different. The constant freezing and thawing of any remaining moisture in the final stages, and the extreme brittleness of the cold rock, would have fractured and weathered the surface in unique ways. The very texture of the mountains and plains would be altered. The landscape would be a testament to the immense power of the cold it had endured. These geological scars would be a permanent memory of the planet's journey. They would be a physical record, written in stone, of the time the world was frozen to its core. Any civilization that might arise on this thawed world would look upon these incredible, unnatural-looking canyons and wonder what immense force could have possibly created them. The scars would be the planet's silent way of telling its own ancient story, a story of a time of absolute stillness and profound fragility. With the return of liquid water, a breathable atmosphere, and a stable climate, the final question of our hypothetical return arises. Could life begin again? The planet would, in many ways, be a hospitable place. The fundamental ingredients for life as we know it, water, organic molecules, and an energy source, would all be present. The organic molecules from the previous biosphere would have been perfectly preserved, enriching the newly thawed oceans and soils. It would be a world filled with the chemical building blocks of life, a rich, primordial soup on a planetary scale. However, the DNA from the previous era of life, though perfectly preserved in the cold, would likely be too damaged by the unshielded cosmic rays that bombarded the planet for eons. The intricate instructions would be fragmented and scrambled. It is unlikely that the old life could simply reawaken. Instead, the planet might be a blank slate, ready for a second genesis. Life would have to begin again from scratch, a new spark of abiogenesis in the warm, nutrient-rich waters. If it did, it would be a completely new tree of life, unrelated to the one that came before. It would evolve on a world with a different geography, a different chemistry. It would be a second, independent experiment in what life can be. Or perhaps life would not return at all. Perhaps the precise conditions that allowed life to begin the first time are so rare that they would not be repeated. The planet might remain a beautiful, dynamic, but sterile world, its oceans and continents empty of life. Our journey ends here, with this open question. We do not need to answer it. It is enough to have arrived at a place of new beginnings. Our thought experiment, which began with an ultimate end, concludes with the gentle, hopeful uncertainty of a new dawn. It leaves us with a sense of the immense resilience of the physical world and the quiet, profound potential for renewal. Our long journey of thought is coming to a close. We have traveled to the impossible floor of temperature and imagined a gentle return. Now, let us return one final time to the state of profound stillness, not to analyze it, but to rest in the serene image it provides, a final, peaceful vision of a world at rest. Let us compose in our minds a final portrait of our Earth at absolute zero. It is a world of sublime and silent beauty. From a distance, it is a perfect sphere, a celestial jewel of pale, bluish white, more brilliant than any planet we have ever seen. Its surface is a near-perfect mirror, reflecting the sharp, unwinking light of the distant sun and the faint, ancient light of the stars and galaxies. It shines with a cold, pure light, a passive beacon in the velvet darkness of space. As we draw closer, we see the immense, dark, fractal canyons that crisscross its surface, the silent, frozen testament to the great shattering of its crust. These are the only features on an otherwise featureless globe, a map of the stresses the world endured in its final surrender. The world is utterly silent. There is no wind, no sound, no vibration of heat. The only motion is the slow, silent turning of the planet on its axis and its stately, eternal orbit around the sun. Beneath the surface, the world is a monument to order. The oceans are a single, solid block of crystal, their depths holding exotic, high-pressure forms of ice. The continents are made of rock that has become as brittle as glass. Deeper still, the mantle and the core are one solid, undifferentiated sphere, the planet's fiery heart having grown still and cold. The entire world, from crust to core, is a single, solid object, its atoms locked in a near-perfect crystalline lattice. And within this perfect structure, a faint, universal hum persists. It is the zero-point energy, the irreducible quantum vibration that is the heartbeat of the still universe. It is a world where all chaos has been smoothed away, leaving only a profound and simple elegance. This final cohesive vision is one of peace. It is not a vision of death, but of completion. It is a world that has reached its final, most stable and most ordered state. It is a crystal floating in the void. In this final vision, we can also see a profound and serene beauty in the physical laws that have shaped this world. Every aspect of the frozen earth is a direct and elegant expression of the fundamental principles of the cosmos. The third law of thermodynamics, which makes the state so difficult to reach, also gives it its special, sacred quality as an ultimate limit. The laws of quantum mechanics, which forbid a state of absolute rest, also gift the silent world with its gentle, eternal, zero-point hum. The principles of crystallography dictate the perfect, ordered arrangement of its atoms. The laws of optics determine its perfect, mirrored surface. The entire planet has become a canvas upon which the laws of nature have painted their masterpiece of simplicity. There is a deep comfort in this. It speaks to a universe that is not random or meaningless, but is underpinned by a deep, mathematical, and predictable order. The transformation of the Earth was not a chaotic event, but a stately, ordered progression, with each step following logically from the last, all of it governed by these eternal and unchanging principles. To contemplate this frozen world is to contemplate the beauty of physics itself. It is to see the abstract equations and principles of science made manifest on a planetary scale. It is a world where there is no more biology, No more geology, no more meteorology, only the pure, fundamental physics of matter and energy in their ground state. This perspective allows us to release any lingering sense of loss or sadness. The beauty of the living, dynamic Earth has been replaced by a different, but no less profound, kind of beauty. The beauty of certainty, of perfection, of a system in complete and total harmony with the laws that govern it. It is the beauty of a problem solved, a journey completed, an equation balanced. It is the quiet, intellectual beauty of physical law itself. As we rest in this final, serene image, we can come to see our frozen Earth as a cosmic monument. Monuments are built to commemorate something, a person, an event, an idea. Our crystalline planet is a monument to one of the most fundamental concepts in the universe, the idea of stillness. In a cosmos defined by motion, spinning galaxies, orbiting planets, energetic stars, vibrating atoms, our Earth has become the ultimate exception. It is a tribute to the state of non-motion, to the absence of change. It stands in stark, silent contrast to the restless energy of the rest of the universe. It is a point of perfect rest in a sea of constant becoming. What does a monument to stillness teach us? It offers a focal point for contemplation, a place for the mind to rest. It reminds us that for all the universe's energy and chaos, there exists a theoretical baseline of perfect peace and order. It is a symbol of the ultimate equilibrium that underlies all things. This monument is not built of carved stone or cast bronze. It is built of the very substance of a world, reformed and perfected by the laws of physics. Its scale is planetary, its craftsmanship is flawless, and its duration is eternal. It is the most magnificent monument imaginable. By framing our final vision in this way, we give it a sense of purpose and dignity. The Earth has not just ended, it has been transformed into a symbol. It has become an object of cosmic significance, a quiet reference point for the entire universe. It is the home of silence, the capital of quiet, the eternal monument to the profound and peaceful beauty of stillness itself. This perspective allows us to leave our thought experiment not with a sense of emptiness, but with a sense of awe and reverence for the simple, profound state the planet has achieved. It is a final, peaceful tribute to the quiet heart of the cosmos. Within this monument to stillness, we discover the final, most profound peace, the absence of time itself. Time, as we experience it, is inextricably linked to change. We perceive time's passage by observing processes, the sun moving across the sky, the hands of a clock turning, the cells in our bodies aging. Time is the measure of change. On a world where no change is possible, the very concept of time loses its meaning. On our Earth at absolute zero, there are no processes. The atoms do not change their position. No chemical reactions occur. No geological forces are at work. The planet is a single, static, unchanging object. For such a world, there is no difference between a second and a billion years. The passage of eons would leave no mark, no record of its passing. The world would be caught in a single eternal moment of now. This is not to say that time stops in a physical sense. The Earth would still travel through space-time on its orbit around the sun. An external observer would still see it moving and could measure the passage of time. But from the perspective of the planet itself, from the framework of its own internal state, time would have become irrelevant. The relentless forward march of the arrow of time, driven by the increase of entropy, would have found its endpoint. With entropy at a minimum and unchanging, the arrow has nowhere left to point. This is a deeply calming concept. It gently dissolves our own sense of time's urgent, forward rush. It invites us to imagine a state of being that is truly timeless, a state of perpetual presence. To contemplate this world is to step, for a moment, outside of the river of time, and to rest on its quiet, peaceful bank. It is the ultimate release from the pressure of becoming, and an immersion in the perfect peace of simply being. As we prepare to leave this timeless, silent world, let us revisit one final idea that imbues it with a sense of profound, quiet power. Let us remember the gentle, persistent hum of zero-point energy. While all thermal, chaotic energy has been removed, the planet is still filled with this fundamental, quantum energy of the ground state. It is not a dead or empty object. It is an object of pure potential. The energy is there, woven into the fabric of its being and the space it occupies. It is an energy that is perfectly ordered, perfectly coherent, and non-dissipative. It is the energy of pure existence. This perspective allows us to see the frozen earth not as an endpoint, but as a foundation. It is the baseline from which all the complex, energetic phenomena of the universe arise. It is a quiet reminder that even in the most still and simple state, the universe is fundamentally energetic and alive. The stillness is not one of emptiness, but of perfect balance. The potential is there, held in a state of perfect, harmonious tension. This final, subtle shift in our perception of the frozen world leaves us with a sense of deep and abiding peace. The world is not gone. It has simply been reduced to its most essential, most fundamental self. It has become a pure expression of the universe's quiet, underlying potential. It is a world at rest, yes, but it is a rest filled with the quiet, powerful hum of all that is, and all that could be. And so, our long and quiet journey comes to its gentle end. We have traveled together in our minds, from a world of warmth and motion to a world of absolute cold and stillness. We have witnessed the freezing of the sky and the sea, the fracturing of the continents, and the silencing of the planet's heart. We have explored the strange and beautiful transformations of matter, and seen our world become a perfect mirror, a silent arc, and a timeless monument. We have approached the impossible, sacred ground of absolute zero, and have found there not an empty void, but a quiet, quantum hum, the fundamental rhythm of the universe itself. And now it is time to let this thought go. Just as our hypothetical Earth radiated its heat away to find a state of peace, we can now allow our minds to release the energy of this exploration. Let the complex ideas gently fade, like ripples on a still pond, leaving only a sense of quiet wonder. The journey was not about the destination of absolute zero, but about the slow, peaceful, and orderly descent. It was a meditation on stillness, on order, and on the simple, elegant laws that govern our cosmos. Our thought experiment has reached its conclusion. The crystalline Earth continues its silent orbit in the quiet space of our imagination, a symbol of ultimate peace and rest. And now, you too can embrace that same sense of peace and rest. You can allow the stillness of that world to become your own. The gentle, universal hum of the cosmos is within you as well. There is nothing more to explore, nothing more to understand. The journey is complete. It is time now, simply, to rest. Tonight, we have journeyed to the theoretical edge of existence, to a place of ultimate quiet and perfect order. We have seen our vibrant world transform into a silent, crystalline sphere, a monument not of loss, but of serene, physical perfection. In this profound stillness, we found not an ending, but a fundamental beginning, the quiet, constant hum of the universe in its purest state. Perhaps our own search for rest is a similar journey. It is a slow letting go of the heat and noise of the day, a gentle descent into our own quiet center. We are all, in our own small way, a part of this vast, silent, and orderly cosmos. And now you have permission to let go of this story, to let go of this thought, and to drift into the peaceful stillness that awaits you. There is nothing left to do but rest. Let the quiet of the cosmos be your own. As you drift peacefully, I have one last gentle question for you to ponder another time. What color do you imagine perfect stillness to be? Thank you for joining me on this quiet journey tonight. If this exploration brought you a sense of calm, a like or subscription helps to support our channel, allowing us to create more peaceful voyages for you. The universe is always here, patiently waiting. When you are ready for another story, you can find our full collection of cosmic narrations in the playlist. For now, however, your journey is complete. Simply rest,